Most people see Mars as just another planet, a rusty, frozen rock floating in space. But what if I told you that beneath that barren surface lies evidence of one of the most dramatic planetary transformations in cosmic history? Picture vast blue oceans stretching to alien horizons. Imagine waves lapping against Martian beaches under foreign skies. Tonight, you'll discover how astronomers uncovered ancient shorelines carved into Mars's northern hemisphere. Coastlines that once bordered seas as massive as Earth's Atlantic Ocean. You'll learn about the slow-motion catastrophe that stripped away everything. The atmosphere, the magnetic field, and finally every last drop of precious water. This isn't just Mars's story. It's a cautionary tale about how fragile planetary habitability really is, how quickly a living world can transform into a frozen monument to environmental collapse. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Mars has been keeping secrets. For decades, the red planet concealed one of the solar system's most extraordinary revelations. The evidence was carved right into its northern plains all along. When spacecraft first began mapping every crater and canyon in unprecedented detail, they uncovered something revolutionary. Ancient shorelines, stretching across an area larger than all of Earth's continents combined. These weren't subtle geological hints that required imagination to interpret. They were massive coastal boundaries that once separated land from a primordial ocean covering nearly half of Mars. The evidence practically screams from the Martian landscape. Orbital cameras mapped coastal terraces, massive channel networks, and sedimentary deposits, all forming unmistakable patterns. Any geologist would recognize these as shoreline geology. They create a continuous coastal perimeter that once encircled 40% of the planet. This marked where an alien ocean met Martian land for millions upon millions of years. Here's what makes this discovery absolutely staggering. If Mars's ancient northern ocean existed today, it would contain enough water to submerge Texas. It would submerge it under 1.6 kilometers of liquid. That's roughly the depth of Earth's North Sea, but it would cover an area comparable to our Pacific Ocean. Close your eyes and imagine standing on those Martian shores 3.5 billion years ago. You'd gaze across water so vast the opposite coastline would vanish beyond the horizon. Alien waves would rhythmically lap against beaches under rust-colored skies. The red planet would have been anything but red. The precision of these coastal features tells us something remarkable. This wasn't some brief flood or temporary wet spell. The shoreline terraces show multiple water levels. Mars's ancient ocean rose and fell like a breathing giant. It responded to climate changes while maintaining its liquid state across entire geological eras. Mars preserved this oceanic fossil record across 3.5 billion years of cosmic bombardment and planet-wide dust storms. It's essentially the ultimate planetary museum. We can still trace the exact geography of an ancient water world that thrived when life was just beginning to stir on our own planet. Standing on Mars today feels like visiting the universe's most devastating vanishing act. 3.5 billion years ago, Mars possessed a body of water comparable in size to Earth's Atlantic Ocean, complete with currents, tides, and an active water cycle. The whole system sustained liquid conditions across the planet's surface for hundreds of millions of years. Today, that magnificent ocean exists only as ghostly water vapor traces. They drift through an atmosphere thinner than Earth's high-altitude stratosphere. Cosmic magic trick gone horribly wrong. The scale of this vanished ocean challenges everything astronomers thought they understood about planetary stability. At its peak, Mars's northern sea contained roughly 20 million cubic kilometers of liquid water. That's enough to create a global ocean 137 meters deep if spread across the entire planet's surface, like cosmic frosting coating everything. Want perspective on that volume? If you could somehow transport Mars's lost ocean to Earth, it would raise the level of all our oceans by 55 meters. Every coastal city on our planet would disappear underwater. New York, London, Tokyo, all submerged. That's how much water simply evaporated into space from our neighboring world. But here's where Mars's story becomes genuinely cosmic tragedy. This wasn't gradual evaporation like a puddle drying in summer heat. Mars suffered a planetary catastrophe that unfolded across hundreds of millions of years, like watching a patient slowly die in geological time. As Mars's magnetic field weakened and eventually flatlined, solar radiation began systematically stripping away the atmosphere, molecule by molecule. With it went the pressure necessary to keep liquid water stable on the surface. The ocean literally boiled away into the vacuum of space, one precious molecule at a time. Evidence of this oceanic apocalypse appears throughout Mars's geology, like chapters in a book of planetary death. Massive outflow channels carved by catastrophic flooding show where the dying ocean made desperate final attempts. Salt deposits concentrated in the northern lowlands mark the last evaporation zones. Here the ocean's remnants became increasingly briny before disappearing entirely. Perhaps most haunting of all, Mars continues losing water to space even today. Roughly 3 million tons per year escape through the upper atmosphere. Like the final drops from a cosmic vessel, we're witnessing the end stages of the largest environmental collapse in our solar system's recorded history. What happens when you fast forward to today's Mars? What remains of that once magnificent water world would make any Earth creature shiver with cosmic despair? The red planet now exists as essentially a giant freezer, set to -60 degrees Celsius permanently. That's cold enough to instantly freeze your breath into ice crystals. They would shatter on the ground like tiny glass beads. The atmospheric conditions on modern Mars read like a recipe for planetary death. Where Earth enjoys a comfortable blanket of 21% oxygen and 78% nitrogen, Mars struggles along with something completely different. The atmosphere is 96% carbon dioxide and thinner than tissue paper. The atmospheric pressure barely registers at 0.6% of Earth's sea level. That means if you somehow teleported to Mars's surface, your blood would literally boil from lack of pressure. No spacesuit, no survival. But here's the truly heartbreaking part about Mars's current water situation. Remember that Atlantic Ocean-sized sea that once dominated the northern hemisphere. Today, the entire planet's atmospheric water content amounts to just 0.03% water vapor. That's roughly equivalent to all the moisture in Earth's atmosphere, compressed into an area the size of Rhode Island. Yet Mars hasn't completely surrendered all its water treasures. The planet hoards its remaining H2O like a cosmic miser, locking it away in polar ice caps and underground deposits. Those gleaming white polar caps that telescopes can spot from Earth contain roughly 5 million cubic kilometers of frozen water and carbon dioxide. Sounds impressive until you realize that's less than 0.25% of what the ancient Northern Ocean once contained. It's like finding loose change after losing your life savings. The temperature swings on modern Mars would break any Earth weather record. Summer at the equator might reach a balmy 20 degrees Celsius during midday, but step into shadow or wait for nightfall. Temperatures plummet to -80 degrees or lower. The thin atmosphere can't retain heat the way Earth's dense atmospheric blanket does. This frozen wasteland represents the final chapter of planetary water loss. Mars transformed from a world where liquid seas lapped against beaches into a cosmic freezer. Now water can only exist as ice or the faintest atmospheric vapor. It's planetary death by 1,000 atmospheric cuts, stretched across billions of years. But picture Earth's entire atmosphere suddenly deciding to go on permanent vacation. That's essentially what happened to Mars, except the process took hundreds of millions of years instead of happening overnight. The numbers tell a story of atmospheric collapse, so complete it's almost hard to believe. 4 billion years ago, Mars enjoyed atmospheric conditions remarkably similar to early Earth. The pressure reached roughly 1 atmosphere, enough to support liquid water across the surface and maintain stable weather patterns. Mars had wind, clouds, possibly even rain. The planet possessed everything necessary for a thriving water world. Fast forward to today. Mars limps along with atmospheric pressure measuring just about 6/1000ths of an atmosphere. That's less than 1% of Earth's current sea level pressure. To put this in perspective, Mars's current atmosphere is thinner than Earth's atmosphere at an altitude of 30 kilometers, well into our stratosphere where only specialized aircraft can operate. This atmospheric diet program from hell happened for several devastating reasons, working in cruel combination. First, Mars is simply too small to hold onto atmospheric gases through gravitational force alone. Earth's mass gives us enough gravitational muscle to grip our atmosphere tightly. Mars, with only 11% of Earth's mass, couldn't maintain the same atmospheric death grip. But size wasn't the only culprit in Mars's atmospheric murder mystery. The planet's magnetic field completely shut down roughly 4 billion years ago. Without this cosmic umbrella, solar wind began systematically stripping away atmospheric particles, like a cosmic leaf blower operating in reverse. The process created a feedback loop of planetary doom. As atmospheric pressure dropped, the temperature required to boil water decreased dramatically. Liquid water became increasingly unstable on the surface. More water vapor escaped to space. Lower atmospheric pressure made liquid water even less stable. The cycle continued relentlessly. Scientists estimate that Mars has lost roughly 99.4% of its original atmosphere to space. That represents one of the most complete atmospheric collapses ever documented in our solar system. Mars essentially went from having weather to having barely any atmosphere at all. The transformation happened surprisingly fast in geological terms. We're not talking about gradual decline over billions of years. The atmospheric collapse accelerated once it began. Mars lost its protective air envelope in what amounts to a geological instant, a planetary atmospheric catastrophe whose timeline we can still read in the rocks today. Despite all this atmospheric and oceanic devastation, Mars has been quietly hoarding a secret. Like a cosmic prepper stockpiling resources for planetary doomsday. The red planet has stashed enormous quantities of frozen water just beneath its dusty surface. This hidden reservoir contains roughly 6 billion tons of ice locked away a mere 1 meter below the ground. That's not a typo. 1 meter. You could dig down with a simple shovel and hit Mars's underground ice vault. This subsurface ice layer stretches across vast regions of the planet like a frozen underground ocean, just waiting for someone to tap into it. For comparison, 6 billion tons of ice represents more water than flows through the Colorado River in 3 years. Recent discoveries have revealed that this underground ice extends far beyond what planetary scientists ever imagined. Radar instruments orbiting Mars have mapped subsurface deposits covering areas equivalent to the combined size of California and Texas. Some regions contain ice layers more than 100 meters thick, essentially underground glaciers that have persisted for millions of years. The ice sits tantalizingly close to the surface because of Mars's unique geological history. As the planet's climate shifted from warm and wet to cold and dry, the last remaining water didn't simply evaporate into space. Much of it soaked into the Martian soil and froze solid, creating a planetary-scale permafrost that has endured across geological ages. This isn't dirty, contaminated ice mixed with Martian soil. Orbital analysis suggests these deposits contain relatively pure frozen water, possibly cleaner than many sources available on Earth. The ice formed from ancient precipitation and groundwater that froze in place as Mars's climate deteriorated. It's essentially fossilized weather from a time when Mars still maintained an active water cycle. But here's what makes these ice deposits truly remarkable for future exploration. Unlike the polar ice caps located thousands of kilometers from potential landing sites, this subsurface ice exists across mid-latitude regions, right where human missions to Mars would most likely establish base camps. Future Mars colonists wouldn't need to haul water across continents. They could literally dig for it in their backyard. Mars decided to carve the most impressive scar in the solar system right across its face, stretching along the planet's equator like a massive gash that refuses to heal. Valles Marineris represents dramatic evidence for ancient water activity. This isn't just another crater from cosmic bombardment. It's a canyon system so enormous it makes Earth's Grand Canyon look like a modest creek bed. The numbers alone tell a story of geological violence on an almost incomprehensible scale. Valles Marineris stretches 4,000 kilometers from east to west. That's roughly the distance from New York to Los Angeles. The canyon plunges up to 7 kilometers deep in some places. Meanwhile, it spans 200 kilometers at its broadest points. If you could somehow transplant this Martian monster to Earth, it would stretch from the Atlantic to the Pacific Ocean. But here's what makes Valles Marineris truly extraordinary for water detectives. The canyon walls display unmistakable evidence of massive water erosion carved over millions of years. Orbital cameras have mapped layer after layer of sedimentary deposits. Stream channels and erosional features cover the walls. These could only form through sustained liquid water flow. The eastern portions show clear outflow channels where catastrophic floods once carved additional pathways toward the northern lowlands. Imagine standing on the rim of this cosmic wound 3 billion years ago. You'd peer down into a canyon system where raging rivers carve through solid rock, like liquid buzzsaws working for millions of years. The scale of water flow required to excavate this much material staggers the imagination. Geologists estimate that some flooding events moved more water in a few months than the entire Colorado River carries in a century. The canyon system connects directly to the ancient Northern Ocean we explored earlier. Valles Marineris essentially functioned as Mars's primary highway for moving water from the planet's interior regions toward the vast seas. It's a fossilized river system preserved on a scale that makes Earth's mightiest waterways seem like gentle streams. What's particularly haunting about Valles Marineris today? The entire canyon system sits bone dry, like discovering the Grand Canyon completely empty of the Colorado River. Every erosional feature, every sedimentary layer, every carved channel tells the story of a world where water once flowed with tremendous power. Across thousands of kilometers of Martian landscape that now knows only silence. What if I told you Mars once possessed a river network so extensive? It would make Earth's Amazon and Mississippi systems combined look like amateur hour. Across the planet's southern highlands, orbital mapping has identified roughly 17,000 individual river valleys carved into the ancient terrain. That's not a rough estimate. That's an actual count of distinct waterways that once flowed across the Martian landscape. These aren't simple straight channels carved by occasional flooding. The Martian river network displays the same complex branching patterns that geologists recognize in Earth's most mature drainage systems. Major rivers collected water from thousands of smaller tributaries. These tributaries themselves gathered flow from countless seasonal streams. The entire system created an intricate web of water circulation. The precision of this ancient hydrological map reveals something remarkable about Mars's former climate. For such an extensive river network to develop, the planet needed sustained precipitation patterns lasting millions of years. You can't carve 17,000 distinct river valleys through brief flooding events. This required a genuine water cycle operating consistently across geological timescales. Many of these ancient rivers stretched for hundreds of kilometers. They connected highland regions to lowland basins in well-organized drainage patterns. Some channels show evidence of seasonal flow variations. This suggests Mars once experienced weather patterns sophisticated enough to support wet and dry seasons. The largest river systems carved valleys several kilometers wide. This indicates water volumes comparable to major Earth rivers during peak flow periods. But here's where the detective work becomes truly fascinating. The River Valley Network preserves a snapshot of Mars's climate history frozen in stone. Older valleys show deeper erosion and more complex branching patterns. This suggests they operated for longer periods under more favorable conditions. Younger channels appear less developed. This indicates that Mars's climate was gradually deteriorating even as some rivers continued flowing. The distribution pattern of these 17,000 waterways tells another crucial story. Most concentrate in the southern highlands. Relatively few appear in the northern lowlands, where the ancient ocean once existed. This suggests that highland precipitation fed river systems that eventually drained into the northern seas, creating a planetary water circulation pattern surprisingly similar to Earth's continental drainage systems. Today, every single one of these 17,000 river valleys sits completely dry. Walking through any of these ancient channels would feel like exploring the dried-up remains of a massive irrigation system, built by some vanished civilization that knew how to move water across entire continents. Deep in Gale Crater, Mars preserved what amounts to a geological library. Each page contains millions of years of ancient water stories written in stone. NASA's Curiosity rover spent years carefully reading these chapters. The robot uncovered evidence of persistent lake conditions that would make any Earth geologist envious. The discovery wasn't subtle. It was written in 3.7 meters of pristine sedimentary layers that could only form under long-term stable water conditions. Gale Crater once hosted a lake roughly the size of Lake Tahoe, complete with seasonal water level changes and sediment deposits that accumulated over millions of years. The crater's central mountain, Mount Sharp, rises 5.5 kilometers above the crater floor, like a massive geological wedding cake where each layer represents a different chapter in Mars's water history, preserved with textbook clarity for billions of years. But the real treasure lies in those clay-rich sedimentary deposits that Curiosity analyzed grain by grain. Clay minerals only form through sustained water-rock interactions lasting thousands of years minimum. You can't fake clay formation through brief flooding or temporary wet periods. The specific types of clay found in Gale Crater require neutral pH conditions and stable temperatures. Essentially a lake environment suitable for life as we know it. The 3.7-meter thickness of these lake bottom deposits tells a story of remarkable environmental stability. Each centimeter represents roughly 1,000 years of sediment accumulation. Simple math reveals that Gale Crater's lake persisted for approximately 3.7 million years minimum, potentially much longer if sedimentation rates varied seasonally. Curiosity's chemical analysis revealed another extraordinary detail. The ancient lake water wasn't acidic or toxic like many extreme environments on Earth. The mineral composition indicates fresh water with low salinity levels. Essentially, the kind of lake where Earth organisms would thrive. The rover even discovered organic compounds preserved in these sedimentary layers. This suggests that Mars's ancient lake environments could have supported complex chemistry. The crater's geology reveals sophisticated water cycling that operated like a planetary-scale fountain. Rivers flowing down from the crater rim deposited sediments that built up the lake bottom layer by layer. Seasonal variations created distinct geological signatures that geologists can still read billions of years later. The entire system functioned as efficiently as Earth's Great Lakes region during optimal conditions. What makes Gale Crater's story particularly poignant? The same location where liquid water once lapped gently against muddy shores for millions of years now experiences daily temperature swings from 20 degrees Celsius to minus 80 degrees Celsius. The lake that once might have sparkled under Martian sunlight exists today only as fossilized memories preserved in stone. Sometimes the smallest details tell the biggest stories. Scattered across Mars's ancient riverbeds, scientists discovered what might be the most intimate evidence of flowing water ever found on another planet. Tiny rounded pebbles, each roughly 2 centimeters in diameter, preserve the biography of individual stones. Stones that tumbled through Martian rivers for over 1,000 kilometers. These aren't just rocks. They're time capsules containing precise records of ancient water flow. On Earth, geologists use pebble roundness as a reliable indicator of transport distance. Sharp, angular rocks become progressively smoother and rounder as rivers carry them downstream. The process requires sustained water flow over vast distances. You simply cannot create perfectly rounded river rocks through brief flooding or occasional water flow. Mars's rounded pebbles display the same textbook characteristics that geologists recognize in Earth's most mature river systems. The stone surfaces show polished smoothness that could only result from prolonged tumbling in flowing water. Chemical analysis reveals that many pebbles originated from highland regions hundreds of kilometers upstream from where rovers discovered them today. These stones essentially hitchhiked across ancient Mars aboard flowing rivers. Each pebble represents an individual journey that took thousands of years to complete. Curiosity rovers' detailed analysis of these pebbles uncovered even more remarkable evidence. Many stones show concentric layering patterns that develop only through prolonged chemical weathering in water-rich environments. Some pebbles contain mineral compositions that require dozens of freeze-thaw cycles to develop properly. Others display coating patterns consistent with seasonal water chemistry changes. But here's what makes these tiny stones truly extraordinary. Each rounded pebble represents an individual journey across ancient Mars. Imagine following one stone's biography. Starting as a sharp fragment breaking off highland cliffs, gradually becoming rounded through countless tumbling kilometers, eventually coming to rest in lowland river deposits, where it waited 3 billion years for Earth robots to discover its story. The distribution patterns of rounded pebbles across Mars provide additional evidence for extensive river networks. Rovers have found similar stones in locations separated by hundreds of kilometers. This suggests that different river systems shared common source regions in the highland areas. Mars once possessed an integrated water circulation system sophisticated enough to transport rocky cargo across continental distances. Today, these same pebbles sit motionless in the Martian dust, like artifacts from a vanished civilization that knew how to move both water and stone across entire planets. No water has moved them for billions of years. They remain as silent witnesses to a time when Mars rang with the sound of flowing rivers carrying stone passengers on journeys that spanned entire continents. Mars kept one final water secret hidden in its northern plains. Evidence that its ancient ocean wasn't some peaceful lake system, but a dynamic body of water capable of generating tsunamis that would terrify any coastal civilization. Orbital mapping has revealed the fossilized remains of tsunami deposits reaching 120 meters above the ancient sea level. That's roughly equivalent to a 40-story building's worth of vertical wave action. These aren't subtle geological hints requiring scientific imagination to interpret. The tsunami deposits appear as distinct geological formations stretching for hundreds of kilometers along what were once Martian coastlines. The wave action was powerful enough to carry massive boulders several kilometers inland from the original shoreline, creating debris fields that geologists can map from orbit with startling clarity. The scale of these ancient Martian tsunamis challenges our assumptions about planetary ocean dynamics. A 120-meter tsunami represents wave energy comparable to the most devastating seismic events in Earth's geological record. For comparison, the 2011 Tohoku tsunami in Japan reached maximum heights of 40 meters. Mars somehow generated wave action 3 times more powerful across an alien ocean billions of years ago. But what could possibly trigger tsunamis of this magnitude on ancient Mars? The most likely culprit involves asteroid impacts directly into the northern ocean. Mars sits much closer to the asteroid belt than Earth. This makes large impacts more frequent and devastating. When a kilometer-sized asteroid slammed into Mars's ancient sea, it would have generated waves that propagated across thousands of kilometers of open water. The tsunami deposits preserve additional evidence of sophisticated ocean dynamics. Geologists can identify at least 2 distinct tsunami events separated by millions of years. This suggests that Mars's ancient ocean remained active long enough to experience multiple catastrophic wave episodes. The sediment patterns show that these weren't brief splash events. They represent sustained wave action that reshaped hundreds of kilometers of ancient coastline. Analysis of the tsunami debris reveals something remarkable about Mars's ancient ocean chemistry. The wave deposits contain mineral compositions indicating that the ocean water remained liquid and relatively fresh during these catastrophic events. This suggests that Mars maintained stable atmospheric conditions during periods when massive waves regularly reshaped its coastlines. The aftermath of these ancient tsunamis would have created temporary inland seas as the massive waves retreated back toward the main ocean. Some of these temporary flood zones appear to have persisted for years or even decades, creating additional lake environments across what are now the dreest regions of Mars. Perhaps most intriguingly, the tsunami evidence suggests that Mars's ancient ocean supported an active geological environment, complete with seismic activity, impact events, and dynamic coastal processes that would have rivaled Earth's most dramatic maritime conditions. This wasn't a stagnant planetary puddle. It was a genuine ocean system with wave action, tides, and catastrophic events that would have made those ancient Martian beaches extremely dangerous places to visit. Today, those same coastal regions where 120-meter tsunamis once thundered against alien shores sit in absolute silence under the thin Martian atmosphere. The only waves that touch these ancient beaches now are gentle dust storms that whisper across the landscape, like ghosts of the mighty waters that once shaped this distant world. Take a deep breath right now. That lungful of air represents luxury that Mars can only dream about, while Earth wraps itself in a thick, protective atmospheric blanket. Mars struggles along with atmospheric conditions so pathetic they'd make a vacuum cleaner jealous. The red planet's current atmospheric pressure measures just 0.6% of Earth's sea level pressure. Essentially, Mars is trying to breathe through a drinking straw. To put this atmospheric poverty into perspective, Mars's current air pressure is thinner than what mountain climbers experience at 35,000 feet above Earth's surface. That's well into the stratosphere where commercial jets cruise, where humans need pressurized cabins to survive. Imagine trying to live permanently at that altitude. Mars makes it even worse by maintaining those conditions everywhere, from sea level equivalents to mountaintops. The comparison becomes truly stark when you consider atmospheric mass. Earth's atmosphere weighs roughly about 5 quadrillion kilograms. Enough gas to create weather patterns, maintain stable temperatures, and protect us from cosmic radiation. Mars's entire atmospheric envelope weighs just 25 trillion kilograms. That's about 200 times lighter than Earth's atmospheric blanket. This atmospheric anorexia creates conditions that would instantly kill any Earth creature. At 0.6% of Earth's pressure, human blood would literally boil from lack of atmospheric compression. Saliva would bubble on your tongue. The moisture in your eyes would vaporize. You'd have roughly 15 seconds of consciousness before the lack of pressure shut down your biological systems entirely. But here's what makes Mars's atmospheric situation particularly tragic. the planet wasn't always this pathetically thin-aired. Geological evidence suggests that ancient Mars once maintained atmospheric pressure roughly similar to Earth's current conditions. The red planet essentially went from having weather to having barely any atmosphere at all. Like watching a balloon slowly deflate over hundreds of millions of years. The current Martian atmosphere consists of 96% carbon dioxide, 1.9% argon, and just 0.16% oxygen. There's more oxygen in Earth's atmosphere at 50,000 feet than in all of Mars's surface air combined. The planet maintains an atmospheric composition that would suffocate Earth life forms, even if pressure levels were adequate. What remains of Mars's atmospheric system barely qualifies as weather. The thin air can't retain heat effectively. This leads to temperature swings that would shatter any Earth ecosystem. Daily temperature variations of 100 degrees Celsius aren't uncommon. The atmosphere lacks the mass necessary to create the stable climate patterns that complex ecosystems require for long-term survival. Right now, as you read these words, Mars is hemorrhaging its remaining atmosphere into space. Like a planetary patient slowly bleeding out in cosmic intensive care, the red planet loses roughly 100 tons of atmospheric gas every single year, a steady, relentless drain that has been ongoing for billions of years. That's equivalent to Mars exhaling a fully loaded Boeing 747 worth of atmospheric mass into the vacuum of space annually. This atmospheric emigration program operates 24 hours a day, 365 days a year. Without vacation breaks or slowdowns, every year Mars loses enough atmospheric material to fill approximately 50 million party balloons. While that might not sound devastating on human timescales, multiply that loss across millions of years. You're looking at atmospheric genocide on a planetary scale. The annual loss rate becomes particularly sobering when you consider Mars's remaining atmospheric reserves. At the current rate of 100 tons per year, Mars would completely lose its existing atmosphere in roughly 250,000 years, if no replacement mechanisms existed. That's essentially tomorrow in geological terms. A cosmic blink of an eye that highlights just how precarious the red planet's atmospheric situation has become. But here's where the mathematics become truly depressing. The 100 tons per year represents Mars's current atmospheric loss rate under today's relatively calm solar conditions. During periods of increased solar activity, Mars's atmospheric loss accelerates dramatically. Solar storms can temporarily boost atmospheric escape rates by factors of 10 or more. When our sun erupts with stronger solar wind and more intense radiation, Mars essentially experiences atmospheric cardiac episodes. The planet loses months' worth of normal atmospheric material in just a few days. This ongoing atmospheric brain drain affects different gas components at different rates. Lighter molecules like hydrogen escape more readily than heavier gases like carbon dioxide. Over geological timescales, this selective loss process gradually changes the atmospheric composition, creating feedback loops that accelerate additional atmospheric escape. Mars essentially experiences atmospheric natural selection, where only the heaviest molecular survivors remain behind. The loss mechanisms operate with ruthless efficiency. Solar ultraviolet radiation breaks apart atmospheric molecules in Mars's upper atmosphere. This creates lighter fragments that more easily achieve escape velocity. Solar wind particles collide with atmospheric gases. They impart enough energy to kick individual molecules out of Mars's gravitational well entirely. The process resembles a cosmic game of atmospheric billiards, with the Sun serving as an opponent that never misses a shot. Scientists estimate that Mars has lost roughly 99% of its original atmosphere through this slow-motion planetary suffocation. The 100 tons per year we observe today represents the final gasps of what was once a thick, Earth-like atmospheric system. We're witnessing the end stages of atmospheric collapse that has been ongoing for over 3 billion years. A planetary death process so gradual that it spans entire geological eras. Mars operates a 2-lane highway system for shipping atmospheric molecules directly into deep space. Business has been booming for billions of years. Atmospheric scientists have identified 2 distinct escape mechanisms that work in combination. They systematically strip away the red planet's remaining air supply. Think of them as different shipping methods for the same tragic cargo: Mars's life-giving atmosphere. The first escape route operates through thermal escape. This functions like a cosmic version of evaporation, high in Mars's upper atmosphere. Solar radiation heats atmospheric molecules until they achieve enough energy to break free from the planet's gravitational grip entirely. Just as water molecules escape from a boiling pot, atmospheric particles gain enough thermal energy to literally fly away into space. This process works most efficiently on lighter gases like hydrogen. They need less energy to achieve escape velocity. The second pathway involves escape, a more violent process that resembles atmospheric kidnapping. Solar wind slams into Mars's upper atmosphere at speeds exceeding 400 kilometers per second. These high-energy collisions strip electrons from atmospheric molecules, creating charged ions that become vulnerable to magnetic forces from the solar wind itself. The charged solar wind then drags these newly created atmospheric ions away from Mars, like cosmic tugboats hauling atmospheric cargo into interplanetary space. The efficiency of both escape mechanisms depends heavily on Mars's lack of a strong magnetic field. Earth's magnetic field creates a protective barrier that deflects most solar wind around our planet, like an umbrella shielding us from cosmic rain. Mars lost its global magnetic field roughly 4 billion years ago. This left the planet's atmosphere completely exposed to solar wind bombardment. Without magnetic protection, both thermal and ion escape processes operate at maximum efficiency. These 2 escape highways don't operate independently. They work together in a coordinated atmospheric removal system. Thermal escape preferentially removes lighter elements like hydrogen. This gradually changes the overall atmospheric composition. Ion escape can remove heavier molecules that thermal processes can't touch, including carbon dioxide and nitrogen. Together, they create a comprehensive atmospheric stripping system, one that leaves virtually no gas molecules safe from eventual space exile. The seasonal variations in these escape processes create additional complexity. During Mars's closer approach to the Sun, increased solar radiation boosts thermal escape rates significantly. Solar storm events can temporarily supercharge ion escape mechanisms, creating massive atmospheric loss events that strip away months' worth of normal atmospheric loss in just a few days. Mars essentially experiences atmospheric weather that determines how quickly it loses its remaining air supply. Recent spacecraft observations have revealed that these escape mechanisms remain surprisingly active even today. NASA's Mavian orbiter has directly observed both thermal and ion escape in real time, watching Mars's atmosphere stream away into space like invisible rivers flowing upward into the cosmic void. We're not just studying ancient atmospheric loss. We're watching it happen right now, molecule by molecule. Physics operates like a cosmic enforcement agency with absolutely no tolerance for rule breaking. Mars learned this lesson the hard way. When atmospheric pressure drops below 1% of Earth's sea level conditions, the fundamental behavior of water changes so dramatically that liquid H2O becomes essentially impossible to maintain on planetary surfaces. Mars crossed this critical threshold billions of years ago. The planet has been living with the consequences ever since. The physics behind this water crisis involves something called the triple point. The specific combination of temperature and pressure where water can exist as liquid, solid, and gas simultaneously. On Earth, this occurs at 0.01 degrees Celsius and 0.6% of standard atmospheric pressure. Below this pressure threshold, liquid water simply cannot remain stable. Regardless of temperature, it either instantly vaporizes into gas or freezes solid into ice. Mars currently maintains atmospheric pressure around 0.6% of Earth's levels. This places the entire planet right at the edge of water's stability zone. The result creates a cosmic catch-22, where liquid water faces instant evaporation during warmer periods, and immediate freezing when temperatures drop even slightly. The planet exists in a permanent state of atmospheric limbo, where water has essentially two choices: become ice or become vapor. But here's where the physics becomes particularly ruthless. Even if you could somehow heat Martian surface water to comfortable Earth-like temperatures, the low atmospheric pressure would cause it to boil violently. Like opening a carbonated beverage in a vacuum chamber. The water wouldn't just warm up. It would immediately transition from liquid to gas phase, creating bubbles and vapor clouds until every drop had evaporated into the thin Martian air. This atmospheric pressure limitation explains why Mars's ancient oceans couldn't survive once the planet's atmosphere began thinning below critical thresholds. As atmospheric loss reduced surface pressure below the 1% mark, existing liquid water faced an impossible choice: freeze into ice deposits or evaporate into space. There was no middle ground where oceans could continue existing as stable liquid bodies. The temperature requirements for liquid water become increasingly demanding as atmospheric pressure decreases. On Earth, water remains liquid across a comfortable range from 0 to 100 degrees Celsius at sea level pressure. On Mars, liquid water requires a much narrower temperature window, essentially a few degrees on either side of the triple point. Any deviation immediately triggers phase changes that eliminate liquid water entirely. Modern Mars occasionally reaches temperatures where water should theoretically remain liquid, particularly during summer days near the equator. However, the combination of low atmospheric pressure and temperature fluctuations means that any liquid water that briefly forms immediately boils away or refreezes within hours. The planet maintains conditions where liquid water can exist only momentarily, before physics intervenes to eliminate it. This pressure limitation creates cascading effects that reinforce Mars's water crisis. As liquid water disappears, atmospheric humidity drops. This reduces atmospheric pressure even further. Lower pressure makes liquid water even more unstable, creating a feedback loop that progressively makes the planet less hospitable to stable water systems. Mars essentially trapped itself in a physics-based death spiral that continues operating today. In 2014, NASA launched the ultimate atmospheric detective to catch Mars red-handed in the act of losing its remaining air supply. The Mavian spacecraft stationed itself in Martian orbit specifically to watch atmospheric escape happen in real time. What it discovered would confirm scientists' worst fears about Mars's ongoing atmospheric collapse. Mavian's instruments detected something both fascinating and tragic. Mars loses approximately 2 kilograms of atmospheric material every single second. That's roughly equivalent to 4 pounds of atmospheric gas streaming away into space faster than you can say atmospheric escape. In the time it takes to read this paragraph, Mars has permanently lost roughly 50 kilograms of its remaining air supply to the cosmic void. The precision of these measurements represents one of the greatest achievements in planetary atmospheric science. MEVIN doesn't just estimate atmospheric loss. It directly observes individual atmospheric particles as they accelerate away from Mars. The spacecraft essentially functions as a cosmic security camera, recording Mars's atmospheric death in unprecedented detail. But Mavian revealed something even more alarming than steady atmospheric loss rates. During solar storm events, when the sun erupts with increased radiation and solar wind activity, Mars's atmospheric loss accelerates dramatically. Mavian has recorded atmospheric escape rates increasing by factors of 10 to 20 during major solar storms. The spacecraft watched Mars' atmospheric material in a few days that would normally require months under calm conditions. The real-time observations show that atmospheric escape isn't some ancient process that ended billions of years ago. Mars continues hemorrhaging atmosphere right now. Every second of every day as you read these words, the planet loses enough atmospheric material in 1 year to fill a volume equivalent to a cube 50 meters on each side. That might not sound massive until you realize this process has been operating for billions of years. Mavian's data confirm that Mars has already lost roughly 99% of its original atmosphere to space. The current atmospheric escape represents the final stages of a planetary catastrophe that began when Mars lost its protective magnetic field. We're witnessing the end game of atmospheric collapse. The last gasps of what was once a thick, Earth-like atmospheric system. The spacecraft's observations also revealed seasonal variations in atmospheric loss that follow predictable patterns. As Mars moves closer to the Sun in its elliptical orbit, atmospheric escape rates increase significantly. During dust storm seasons, when Mars's thin atmosphere absorbs more solar energy, escape rates accelerate even further. The planet experiences atmospheric weather that directly affects how quickly it loses its remaining air supply. Perhaps most sobering, Mavian's measurements suggest that Mars's current atmospheric loss rate could continue for millions of years. Without completely stripping away the remaining atmosphere, the red planet maintains just enough atmospheric mass to sustain slow but steady loss for geological ages to come. Mars faces an extended future of gradual suffocation rather than immediate atmospheric death. A slow-motion planetary tragedy that will continue long after human civilization has disappeared from Earth. Somewhere around 4 billion years ago, Mars experienced the cosmic equivalent of a planetary power grid failure. The planet's magnetic field had been operating reliably for hundreds of millions of years. Its invisible protective shield simply switched off like someone flipping a circuit breaker. This wasn't a gradual decline or slow weakening process. Mars's magnetic field essentially suffered a catastrophic system failure that has never been repaired. The timing of this magnetic shutdown couldn't have been worse for Mars's long-term survival prospects. The magnetic field collapse occurred just as the young solar system was settling into more stable conditions. It happened precisely when Mars needed maximum protection to maintain its developing atmosphere and water systems. Instead of enjoying billions of years of magnetic protection like Earth, Mars lost its defensive systems right at the beginning of planetary adolescence. But what exactly caused Mars's magnetic field to fail so completely? The answer lies deep within the planet's interior. It is where a sophisticated electromagnetic generator once operated with clockwork precision. Mars's magnetic field originated from churning motions in its molten iron core, the same process that generates Earth's protective magnetic field today. For this system to work properly, the planetary core must remain hot enough to stay liquid. It must maintain convective currents that generate electrical activity. Mars faced a fundamental size disadvantage in this cosmic protection game. The red planet contains only 11% of Earth's mass. This meant its interior cooled much faster than our planet's massive core. Think of it like comparing a small campfire to a large bonfire. The smaller fire burns out much sooner because it contains less fuel and loses heat more rapidly to the surrounding environment. As Mars's core gradually cooled below critical temperatures, the convective currents that generated the magnetic field began slowing down. Eventually, they stopped entirely. The planet's electromagnetic generator essentially ran out of fuel and shut down permanently, without ongoing electrical activity in the core. Mars lost the magnetic field that had been protecting its atmosphere and surface from solar radiation. The magnetic field collapse created immediate consequences for Mars's atmospheric stability. Solar winds suddenly gained direct access to Mars's upper atmosphere without any magnetic barriers to deflect the cosmic bombardment. The planet went from having comprehensive protection against space weather to being completely defenseless against solar radiation. It happened in what amounts to a geological instant. Evidence of this ancient magnetic shutdown appears throughout Mars's geological record. Like a crime scene frozen in stone, rocks formed before the magnetic collapse show strong magnetic signatures. Younger geological formations display virtually no magnetic properties. Mars essentially preserved the exact moment when its protective systems failed. It created a planetary fossil record of electromagnetic death that scientists can study billions of years later. The moment Mars lost its magnetic field, the planet became a sitting duck in a cosmic shooting gallery. Solar wind gained unrestricted access to Mars's atmosphere and surface. This relentless stream of charged particles flows from the Sun at over 400 kilometers per second. Imagine removing the roof from your house during a perpetual hailstorm, except the hail consists of high-energy particles traveling at speeds that would circumnavigate Earth in less than 2 minutes. This solar wind bombardment operates with the consistency of a cosmic sandblaster that never takes breaks. Every second of every day for the past 4 billion years, charged particles have been pummeling Mars's upper atmosphere. They carry enough energy to systematically strip away atmospheric molecules. The bombardment intensity varies with solar activity, but it never stops completely. Mars essentially became a target in a cosmic firing range with no way to take cover. The physics of this atmospheric destruction process works with devastating efficiency. When high-speed solar wind particles collide with atmospheric molecules, they transfer energy. They kick individual gas particles out of Mars's gravitational well. It's like playing cosmic pool, where each solar wind impact can send atmospheric molecules flying off into deep space. Over millions of years, this particle-by-particle removal process has stripped away most of Mars's original atmosphere. Without magnetic field protection, Mars also became vulnerable to solar storms. These are massive eruptions of charged particles and radiation that periodically blast outward from the Sun's surface. During these cosmic tempests, atmospheric loss rates can increase by factors of 10 or more. This happens as intensified solar wind overwhelms Mars's remaining atmospheric defenses. The planet experiences space weather with no umbrella for protection. The solar wind bombardment affects different atmospheric components in various ways. It creates a selective stripping process that gradually changes atmospheric composition over geological time. Lighter gases like hydrogen escape more easily than heavier molecules like carbon dioxide. But given enough time and energy, solar wind can remove virtually any atmospheric component. Mars lost atmospheric diversity as well as atmospheric mass. The bombardment also affects Mars's surface directly. This is because the thin remaining atmosphere provides minimal protection against charged particle radiation. Any complex organic molecules that might have formed on ancient Mars faced continuous destruction from solar wind impacts. This radiation would prove lethal to most Earth life forms. This defenseless exposure to solar wind continues today. It has been stripping away Mars's atmosphere for billions of years. Current spacecraft orbiting Mars can observe solar wind particles streaming directly into the planet's upper atmosphere. They watch atmospheric destruction happen in real time. We're not studying ancient atmospheric loss. We're witnessing ongoing planetary suffocation that shows no signs of slowing down. While Mars suffers under constant solar wind bombardment, Earth enjoys premium cosmic protection courtesy of a magnetic field system that has been operating reliably for over 3.5 billion years. Our planet's magnetic field strength measures roughly 50 microteslas at the surface. Enough magnetic force to deflect solar wind particles traveling at 400 kilometers per second around our planet. Like cosmic traffic flowing around a magnetic island, this invisible protective system extends far beyond Earth's atmosphere. It creates a massive magnetic bubble called the magnetosphere that stretches over 60,000 kilometers into space. Solar wind particles approaching Earth encounter this magnetic barrier. They get swept around our planet rather than directly impacting our atmosphere. It's like having a cosmic umbrella that automatically deflects space weather away from our planetary home, without requiring any maintenance or energy input from human civilization. The magnetosphere deflection system works with elegant simplicity. Charged solar wind particles cannot easily cross magnetic field lines, so they follow the curved paths of Earth's magnetic field around the planet toward the polar regions. Most solar wind gets channeled harmlessly past Earth and continues flowing into deep space. Only a small fraction manages to penetrate the magnetic defenses and interact with our upper atmosphere. Earth's magnetic field strength remains remarkably stable compared to the catastrophic collapse that Mars experienced billions of years ago. While our magnetic field does undergo periodic reversals every few 100,000 years, it never shuts down completely like Mars's system did. During reversal periods, the field's strength decreases but doesn't disappear entirely. It still provides protection against the worst solar wind bombardment. The daily protection service that Earth's magnetosphere provides would be impossible to replace with any human technology. The energy required to artificially generate a planetary-scale magnetic field would exceed the total power output of human civilization by enormous margins. We essentially live inside a natural force field that operates automatically and costs nothing to maintain, protecting billions of people from lethal cosmic radiation exposure. When Earth's magnetic defenses occasionally fail during extreme solar storm events, the results demonstrate just how crucial this protection system really is. Major solar storms can temporarily overwhelm the magnetosphere, allowing charged particles to penetrate deeper into our atmosphere. This disrupts satellite communications, power grids, and electronic systems. These brief glimpses of reduced magnetic protection highlight how vulnerable Earth would become without our magnetic shield. The polar auroras that create beautiful light displays in northern and southern skies as actually the visible evidence of our magnetic protection system working properly. These colorful lights appear when solar wind particles that penetrate the magnetic defenses collide with atmospheric gases near the polar regions. The auroras essentially mark the locations where Earth's magnetic field channels cosmic bombardment away from populated areas, toward uninhabited polar regions where the light shows can safely occur. Without this 50 microtesla magnetic umbrella service, Earth would face the same atmospheric stripping process that has been devastating Mars for billions of years. Our planet's thick atmosphere would gradually erode under constant solar wind bombardment. Ocean levels would drop as water vapor escaped to space. Complex life would struggle to survive under increased cosmic radiation exposure. Earth's magnetic field represents the difference between planetary habitability and cosmic sterilization. Mars may have lost its global magnetic field billions of years ago, but the red planet preserved evidence of its former magnetic glory in the most permanent archive possible: the rocks themselves. Scattered throughout Mars's southern hemisphere, ancient geological formations contain fossilized magnetic signatures. They tell the story of a planet that once possessed protective magnetic shielding comparable to Earth's current system. These magnetic fossils formed through a process that works like cosmic recording technology embedded in stone. When volcanic rock crystallizes from molten material, iron-bearing minerals align themselves with the surrounding magnetic field, like tiny compass needles frozen in place. Once the rock solidifies, these magnetic orientations become permanently locked in the crystal structure. This creates a geological record of ancient magnetic field conditions that can persist for billions of years. The magnetic signatures preserved in Mars's southern highlands reveal something remarkable about the planet's former magnetic capabilities. The rock formations display magnetic field strengths that rival Earth's current protective system. This suggests that ancient Mars once enjoyed comprehensive magnetic shielding against solar wind bombardment. These weren't weak, local magnetic anomalies. They represent evidence of a robust, planet-wide magnetic field system. But the geographic distribution of these magnetic fossils tells an additional story of planetary magnetic death. The strongest magnetic signatures concentrate in the southern hemisphere. This is especially true in the oldest geological formations dating back over 4 billion years. Northern hemisphere rocks formed after the magnetic field collapse show virtually no magnetic properties. Mars essentially preserved a geological timeline of its magnetic field shutdown. The magnetic archive reveals that Mars's ancient field operated with sophisticated structure similar to Earth's current magnetosphere. The fossilized magnetic orientations show evidence of magnetic pole reversals and field strength variations. This indicates a dynamic, active magnetic system. Ancient Mars possessed the same type of magnetic field complexity that currently protects Earth from cosmic radiation bombardment. Orbital magnetic surveys have mapped these ancient signatures with remarkable precision. They create detailed maps of where Mars's magnetic field once existed and how strong it used to be. The magnetic fossil record shows that some regions maintain magnetic field strengths exceeding 100 nanoteslas. This is roughly twice Earth's current surface field strength. Mars once had magnetic protection that surpassed what Earth enjoys today. The preservation of these magnetic memories in Martian rocks provides scientists with a unique window into planetary magnetic field evolution. No other planet in our solar system has maintained such a complete geological record of magnetic field operation and subsequent collapse. Mars accidentally created the ultimate magnetic field museum. Here, scientists can study billions of years of electromagnetic history preserved in stone. Perhaps most tantalizingly, the magnetic fossil record suggests that Mars's magnetic field didn't fail gradually over millions of years. The geological evidence points toward a relatively rapid collapse that occurred over timescales short enough to be preserved distinctly in the rock record. Mars lost its magnetic protection in what amounts to a geological instant. It was a planetary electromagnetic catastrophe whose evidence remains frozen in the planet's ancient stones. It is waiting for Earth scientists to decode the magnetic memories of a world that once possessed the protective shielding it desperately needed to survive. Size matters in the cosmic neighborhood, and Mars drew the short straw in planetary mass distribution. Earth tips the cosmic scales at a respectable mass of about 6 times 10 to the 24 kilograms. Mars struggles along with just 11% of that mass, roughly 6.4 times 10 to the 23 kilograms. That might sound like splitting hairs when dealing with planetary scale numbers. But this size disadvantage created a gravitational weakness that has been sabotaging Mars's survival prospects for billions of years. The gravitational consequences of Mars's lightweight status become immediately apparent when you consider surface gravity measurements. Earth maintains a robust 9.8 meters per second squared of gravitational acceleration, enough to keep our atmosphere locked in place and our oceans from floating away. Mars limps along with just 3.7 meters per second squared, creating surface conditions where everything weighs roughly 38% of its Earth equivalent. This gravitational diet program might sound appealing if you're trying to break personal weightlifting records, but it creates devastating consequences for planetary atmospheric retention. Atmospheric molecules need gravitational force to remain bound to a planet's surface rather than drifting off into space. Mars's weak gravity provides insufficient holding power to maintain thick atmospheric layers, especially when combined with solar wind bombardment and thermal heating effects. The relationship between planetary mass and gravitational strength follows cosmic laws that Mars simply cannot overcome through willpower or good intentions. Gravity strength depends directly on planetary mass and decreases rapidly with distance from the planetary center. Mars's smaller mass generates weaker gravitational fields at every altitude. making it progressively easier for atmospheric particles to achieve escape velocity and flee to deep space. But Mars's mass disadvantage extends beyond simple gravitational weakness. Smaller planets cool more rapidly than larger worlds because they have less internal heat to begin with. They also have greater surface area relative to their volume. Think of Mars as a cosmic cupcake compared to Earth's layer cake. The smaller dessert cools off much faster after being removed from the oven. This rapid cooling affects everything from magnetic field generation to volcanic activity. The gravitational weakness also affects Mars's ability to capture and retain water vapor in its atmosphere. Water molecules, being relatively light, escape more easily from weak gravitational fields. As Mars's atmospheric pressure decreased due to ongoing atmospheric loss, the remaining water became even more vulnerable to gravitational escape. The planet essentially lost its grip on the very molecules necessary for maintaining liquid water on its surface. Modern Mars demonstrates the long-term consequences of operating with insufficient gravitational muscle. The planet maintains atmospheric pressure at just 0.6% of Earth levels. Weak gravity cannot prevent atmospheric escape during solar wind bombardment. Mars's gravitational handicap created a feedback loop where atmospheric loss made the remaining atmosphere even more vulnerable to additional loss mechanisms. This cosmic size disadvantage represents a permanent planetary characteristic that Mars can never overcome. Atmospheric loss or magnetic field collapse might theoretically be addressed through advanced technology. Gravitational strength depends entirely on planetary mass. Mars will maintain weak surface gravity for the remainder of its existence, making the red planet permanently unsuitable for retaining thick atmospheres or stable liquid water systems without artificial assistance. Every planet operates as a gravitational prison designed to keep atmospheric molecules from escaping into space. But Mars runs what amounts to a minimum security facility with remarkably lax escape policies. The red planet's escape velocity measures just 5.03 kilometers per second, the speed required for any object to break free from gravitational bonds. That's fast enough to cross the United States in about 10 minutes, but pathetically slow compared to the cosmic incarceration standards that successful planets maintain. Earth operates a more secure gravitational detention system with an escape velocity of 11.2 kilometers per second, more than twice Mars's atmospheric holding power. This difference means that atmospheric molecules need roughly 4 times less energy to escape from Mars than from Earth. In cosmic prison terms, Mars essentially installed a revolving door where Earth built maximum security walls. The escape velocity mathematics work against Mars in multiple devastating ways. Atmospheric particles gain energy from solar heating, molecular collisions, and electromagnetic interactions. On Earth, most atmospheric molecules never accumulate enough energy to achieve the 11.2 kilometers per second speed required for escape. On Mars, the lower escape velocity means the same energy sources can accelerate atmospheric particles more easily. They can pass the 5 kilometers per second threshold for permanent departure. This gravitational weakness becomes particularly problematic for lighter atmospheric components like hydrogen and water vapor. These molecules require less energy to achieve high speeds due to their lower masses, making them preferentially vulnerable to escape from weak gravitational fields. Mars essentially operates a selective atmospheric prison system. It fails to contain the lighter gases most crucial for maintaining water cycles and atmospheric complexity. The escape velocity disadvantage compounds over geological timescales through cumulative atmospheric loss. Each escaped molecule represents permanently lost atmospheric mass. This slightly reduces the planet's total gravitational field strength. While individual molecular escapes don't significantly affect planetary mass, billions of years of steady atmospheric loss create measurable reductions in Mars's gravitational holding power. Solar wind bombardment exploits Mars's weak escape velocity with devastating efficiency. High-energy particles from the Sun can impart enough additional speed to atmospheric molecules that can push them beyond the 5 kilometers per second escape threshold. Earth's higher escape velocity provides a larger energy buffer that protects atmospheric molecules from solar wind acceleration effects. The thermal escape process operates like a molecular lottery where Mars consistently draws losing tickets. Atmospheric heating from solar radiation creates temperature distributions where some molecules achieve velocities approaching escape speed. In Mars's weak gravitational field, relatively modest additional energy inputs can push these heated molecules beyond the escape velocity threshold. Earth's stronger gravity requires much more extreme heating to achieve atmospheric escape. Mars's escape velocity also affects the planet's ability to retain atmospheric gases delivered by comets, asteroids, and volcanic outgassing. Earth's strong gravitational field can capture and retain gas molecules from these sources. Mars's weak escape velocity means many potentially valuable atmospheric additions simply pass through the planet's gravitational well without becoming permanently incorporated into the atmospheric system. The red planet essentially operates a leaky bucket that cannot hold on to atmospheric resources even when external sources attempt to replenish them. Mars measures just 3.4 thousand kilometers from center to surface, roughly half Earth's 6.4 thousand kilometer radius. This size difference might seem like a simple scaling issue, but it created fundamental thermal problems that doomed Mars's long-term geological activity. Small planets face an unavoidable cosmic curse. They cool off much faster than large worlds, leading to premature shutdown of the internal processes that keep planets geologically alive. The physics behind planetary cooling follow the same principles that make small coffee cups cool faster than large thermoses. Mars possesses less internal volume to store heat, but relatively more surface area through which to lose that heat to space. The surface area to volume ratio works against small planets like a cosmic energy drain that operates more efficiently on smaller worlds. Mars essentially started life as a planetary system destined for early thermal retirement. When planets first form, they accumulate enormous amounts of heat from multiple sources. Gravitational compression, radioactive decay, and impact energy from ongoing bombardment. Earth's large mass allowed it to retain this thermal energy for billions of years, maintaining the internal temperatures necessary for ongoing volcanic activity, plate tectonics, and magnetic field generation. Mars's smaller thermal reservoir meant it burned through its geological fuel supply much more rapidly. The consequences of rapid cooling appear throughout Mars's geological record like chapters in a book of premature planetary aging. Early Mars maintained vigorous volcanic activity, extensive lava flows, and dynamic geological processes that created diverse surface features. But as the planet's interior cooled below critical thresholds, volcanic activity decreased dramatically. Tectonic processes slowed to a crawl. Geological activity essentially entered permanent hibernation. This thermal shutdown affected Mars's magnetic field generation more severely than any other planetary system. Magnetic fields require hot, convecting liquid metal in planetary cores to generate the electrical currents that create electromagnetic shielding. As Mars's core cooled and partially solidified, the convective processes that maintained magnetic field generation gradually weakened and eventually stopped entirely. The planet's electromagnetic heart essentially experienced thermocardiac arrest. The cooling process also affected Mars's ability to maintain active volcanic outgassing that could potentially replenish atmospheric losses. Earth's ongoing volcanic activity continuously adds water vapor, carbon dioxide, and other gases to the atmosphere, helping to replace molecules lost to space. Mars's volcanic systems largely shut down billions of years ago, eliminating a crucial atmospheric resupply mechanism just when the planet needed it most. Mars's rapid cooling created a cascade of geological failures that reinforced each other in destructive feedback loops. Loss of internal heat led to magnetic field collapse. That increased atmospheric loss rates and reduced surface pressure. Lower pressure made liquid water unstable. It also eliminated water-based geological processes that might have helped retain atmospheric moisture. The planet's small size triggered a sequence of geological dominoes that toppled Mars's entire environmental system. Modern Mars maintains a core temperature around 1600 degrees Celsius, still hot enough to melt lead, but not hot enough to sustain the convective processes necessary for magnetic field generation or vigorous volcanic activity. The planet exists in geological semi-retirement, warm enough to prevent complete thermal death, but too cool to maintain the active geological processes that created its former water-rich environment. Mars essentially became a cosmic senior citizen that retired from active planetary duty billions of years earlier than Earth's geological career timeline. Deep beneath Mars's rusty surface, the planet's core maintains a temperature of roughly 1600 degrees Celsius, hot enough to melt copper and vaporize zinc, but tragically inadequate for the cosmic job it's supposed to perform. This core temperature represents the thermal graveyard where Mars's magnetic field generator finally gave up and died, leaving the red planet defenseless against solar wind bombardment for the past 4 billion years. The magnetic field generation process requires core temperatures hot enough to maintain vigorous convective motion in liquid metal. Earth's core reaches temperatures exceeding 5,000 degrees Celsius, nearly as hot as the sun's surface. This drives powerful circulation patterns in molten iron that generate our protective magnetic field. Mars's comparatively cool core temperature creates sluggish convective motion that lacks the energy necessary to sustain electromagnetic field generation. But core temperature tells only part of Mars's magnetic field mortality story. The planetary dynamo process requires not just hot metal, but liquid metal moving in organized convective patterns. As Mars's core cooled below critical thresholds, parts of the interior began solidifying. This disrupted the fluid motions necessary for magnetic field generation. The planet's electromagnetic generator essentially clogged up with solidified metal components. The transition from magnetically active to magnetically dead occurs at specific temperature thresholds that Mars crossed billions of years ago. When core temperatures drop below approximately 2,000 degrees Celsius, convective motions become too weak and irregular to maintain coherent magnetic fields. Mars's current 1600-degree core temperature sits well below this critical threshold, explaining why the planet shows no signs of magnetic field recovery. Earth's magnetic field continues operating successfully because our planet's massive size allows it to retain core temperatures well above the dynamo threshold. Our core remains hot enough to drive vigorous convective circulation that generates magnetic field strength measuring 25 to 65 microteslas at the surface. Mars's weak core temperature produces virtually no magnetic field activity, less than 1% of Earth's protective strength in most locations. The core cooling process that killed Mars's magnetic field represents irreversible planetary aging that cannot be reversed through any natural mechanism, unlike atmospheric loss, which could theoretically be replenished through volcanic outgassing or external sources. Core temperatures can only decrease over cosmic timescales. Mars will never again achieve the internal thermal conditions necessary for magnetic field generation. The magnetic field death created cascading effects throughout Mars's environmental systems. Without magnetic protection, solar wind gained direct access to Mars's upper atmosphere. This accelerated atmospheric loss rates and reduced surface pressure. Lower atmospheric pressure made liquid water unstable. This eliminated surface water cycles that might have helped cool the planet's surface and maintain thermal regulation systems. Mars's core temperature story also reveals why the planet's magnetic field collapse occurred relatively suddenly in geological terms. As cooling progressed and core temperatures approached critical thresholds, the dynamo process became increasingly unstable. Small additional temperature decreases pushed the system beyond operational limits. This caused rapid magnetic field decay rather than gradual weakening. Mars experienced electromagnetic cardiac arrest rather than slowly declining magnetic health. The current 1600-degree core temperature ensures that Mars will remain magnetically dead for the remainder of its existence. Even if external energy sources somehow warmed the planet's surface, the core would require millions of additional degrees to restart dynamo processes. Mars's electromagnetic generator suffered permanent thermal shutdown that has condemned the red planet to billions of additional years without magnetic protection, against the hostile space environment that continues eroding its remaining atmospheric reserves. Location determines everything in cosmic real estate. The three most important factors that doomed Mars to permanent energy poverty from the moment the solar system finished forming. Mars is positioned 1.5 astronomical units from the Sun. Earth sits at a prime 1 astronomical unit. Mars receives just 57% of the solar energy that powers Earth's climate system. This 43% solar energy deficit created a permanent heating disadvantage. It has been sabotaging Mars's atmospheric and water retention efforts for billions of years. The solar energy mathematics work according to cosmic laws that Mars cannot negotiate or overcome through planetary determination. Solar radiation intensity decreases with the square of distance from the energy source, creating dramatic energy differences across relatively modest distance changes. Mars's extra 1/2 astronomical units distance from the Sun translates into receiving less than half the energy per square meter that Earth enjoys. Roughly 75 million kilometers of additional distance makes the difference between planetary habitability and cosmic energy poverty. This solar energy deficit affects every aspect of Mars's environmental systems, like a cosmic utility bill that the planet cannot afford to pay. Reduced solar heating means lower atmospheric temperatures. This decreases molecular motion and reduces the energy available for atmospheric circulation patterns. Cooler temperatures also make liquid water less stable, requiring higher atmospheric pressures to prevent immediate freezing or boiling. The energy shortage becomes particularly devastating when combined with Mars's other planetary handicaps. While Earth receives abundant solar energy to drive atmospheric heating and circulation, Mars must operate its environmental systems on a severely restricted energy budget. The planet essentially tries to maintain atmospheric dynamics and water cycles while running on cosmic economic hardship conditions. Solar energy drives the atmospheric escape mechanisms that have been stripping away Mars's remaining air supply for billions of years. However, the reduced energy input means that thermal escape processes operate less efficiently on Mars than they would at Earth's distance. This creates the cosmic irony that Mars receives enough solar energy to slowly destroy its atmosphere, but not enough to maintain stable environmental conditions. The 43% solar energy deficit also affected Mars' early atmospheric evolution when the planet still maintained thicker atmospheric conditions. Reduced solar heating meant that ancient Mars required higher concentrations of greenhouse gases like carbon dioxide to maintain temperatures suitable for liquid water. When atmospheric loss reduced greenhouse gas concentrations, the solar energy deficit made it impossible for Mars to compensate through increased solar heating. Seasonal variations compound Mars's energy problems through orbital eccentricity effects that create dramatic changes in solar energy reception throughout the Martian year. Mars's elliptical orbit carries the planet from 1.38 to 1.67 astronomical units distance from the Sun, creating seasonal energy variations that range from 31% below to 51% below Earth's energy reception levels. These extreme seasonal swings make it even more difficult for Mars to maintain stable environmental conditions. The solar distance disadvantage also affects atmospheric heating patterns that drive weather systems and atmospheric circulation. Earth's abundant solar energy creates vigorous atmospheric mixing, storm systems, and circulation patterns that help distribute heat around the planet. Mars's energy-starved atmosphere maintains much weaker circulation patterns, creating temperature extremes and atmospheric stagnation that further destabilize environmental conditions. This solar energy poverty represents another permanent planetary characteristic that Mars cannot overcome without relocating to a different orbital position. Atmospheric loss or magnetic field collapse might theoretically be addressed through advanced technology. Orbital mechanics operate according to cosmic laws that require enormous energy inputs to modify. Mars remains permanently sentenced to receiving insufficient solar energy to maintain the environmental conditions necessary for stable liquid water systems or thick atmospheric retention. Picture Mars 4.5 billion years ago, and you'd barely recognize the planet that now serves as a cosmic freezer. During this golden age of Martian climate, the red planet enjoyed atmospheric pressure measuring a full 1 atmosphere, exactly matching Earth's current sea level conditions. Average global temperatures hovered around a comfortable 15 degrees Celsius, creating surface conditions where liquid water could flow freely across continents and pool in vast ocean basins. Without any fear of boiling away or freezing solid, this wasn't just a brief warm spell or temporary climatic accident. Mars maintained these Earth-like conditions for hundreds of millions of years during the early solar system's most chaotic period. While asteroids and comets bombarded both planets with devastating regularity, Mars possessed all the environmental systems necessary to maintain stable climate conditions. Despite cosmic violence occurring throughout the solar system, the atmospheric composition during Mars's golden age created a natural greenhouse effect that kept surface temperatures well above freezing. The planet's thick atmosphere contained substantial concentrations of carbon dioxide, water vapor, and other greenhouse gases. These trapped solar radiation efficiently. Mars operated a planetary heating system sophisticated enough to maintain liquid water stability across its entire surface, from equatorial regions to polar zones. But what made this golden age truly remarkable was Mars's integrated environmental system operating at peak efficiency. The planet maintained active volcanic outgassing that continuously replenished atmospheric gases lost to space. A robust magnetic field provided comprehensive protection against solar wind bombardment. Vigorous atmospheric circulation patterns distributed heat around the planet. This prevented extreme temperature variations that might destabilize water systems. The water cycle during this period functioned with Earth-like complexity and reliability. Evaporation from vast northern oceans created cloud systems that transported moisture to highland regions, where precipitation fed the extensive river networks that carved those 17,000 valleys we discussed earlier. Seasonal variations created weather patterns sophisticated enough to support diverse geological processes and potentially complex chemistry. Mars's golden age surface pressure of 1 atmosphere provided crucial protection for liquid water stability. At this pressure level, water remains liquid across the familiar 0 to 100 degrees Celsius range, creating enormous environmental flexibility for maintaining stable water systems. The thick atmosphere also provided protection against cosmic radiation and meteorite bombardment that would have sterilized thinner atmospheric systems. The planet's gravitational field, while weaker than Earth's, proved initially adequate for retaining this thick atmospheric envelope. Mars's magnetic field deflected solar wind efficiently enough to prevent catastrophic atmospheric loss. The combination of adequate gravity, magnetic protection, and continuous atmospheric replenishment through volcanic activity created a stable system, one that could have theoretically operated for billions of years under ideal conditions. This golden age represents the baseline for understanding just how far Mars has fallen from its former environmental glory. The planet that once maintained conditions suitable for Earth-like weather patterns now struggles to retain an atmosphere thinner than Earth's stratosphere. Mars transformed from a world where liquid water was abundant and stable into a cosmic monument to environmental collapse. A transformation that took billions of years to complete. 4 billion years ago, Mars experienced what might be the most consequential power failure in planetary history. The planet's magnetic field had been protecting the atmosphere from solar bombardment for hundreds of millions of years. Its invisible shield suddenly shut down like a cosmic circuit breaker tripping under overload. This magnetic field collapse triggered stage 1 of Mars's atmospheric death sentence. beginning a process that would eventually strip away 99% of the planet's protective air envelope. The magnetic shutdown didn't cause immediate atmospheric catastrophe, but it opened the door for cosmic vandalism that would continue for billions of years. Solar winds suddenly gained unrestricted access to Mars's upper atmosphere. Charged particles streaming from the sun at over 400 kilometers per second now had a clear path to the planet's air supply. What had previously been a protected atmospheric system became a sitting duck in a cosmic shooting gallery. With no way to take cover, the initial atmospheric loss rates during Stage 1 remained relatively modest by cosmic standards. Mars lost perhaps thousands of tons of atmospheric material annually, rather than the hundreds of tons per year that characterize modern atmospheric escape. However, this seemingly gentle atmospheric bleeding represents the beginning of an irreversible process, one that would gradually accelerate as protective atmospheric layers thinned and became increasingly vulnerable to solar bombardment. The loss process operated with selective efficiency that preferentially removed lighter atmospheric components. Hydrogen and water vapor molecules, being relatively light, escaped more readily than heavier gases like carbon dioxide and nitrogen. This selective stripping gradually changed Mars's atmospheric composition, reducing the concentration of greenhouse gases that helped maintain warm surface temperatures. Stage 1 atmospheric loss created the first subtle signs of climate deterioration that would eventually do Mars's water systems. Atmospheric pressure began dropping from the comfortable 1 atmosphere levels that had maintained stable liquid water conditions. Surface temperatures started experiencing greater daily and seasonal variations as the thinning atmosphere lost heat retention capacity. The feedback loops that would eventually accelerate atmospheric loss began operating during this initial stage. As atmospheric pressure decreased, water vapor became more vulnerable to escape processes. Reduced water vapor concentrations meant less atmospheric greenhouse heating. This slightly cooled surface temperatures. Cooler temperatures reduced evaporation rates, which further decreased atmospheric humidity levels. But Mars still maintained enough atmospheric mass during Stage 1 to support active weather systems. Liquid water stability continued across most of the planet's surface. The Northern Ocean continued operating normally. River systems maintained flow patterns. Seasonal variations continued supporting complex geological processes. To a casual observer, Mars would have appeared largely normal despite the underlying atmospheric vulnerability. The magnetic field loss that triggered Stage 1 represented a point of no return for Mars's long-term environmental prospects. Without magnetic protection, the planet could no longer prevent atmospheric loss, regardless of how much volcanic outgassing might attempt to replenish the escaping gases. Mars essentially developed a chronic atmospheric bleeding condition that no natural healing process could cure. The red planet had crossed the threshold from environmental stability into irreversible decline, a decline that would continue operating for billions of years. By 3.8 billion years ago, Mars had crossed a critical environmental threshold that sealed the planet's fate as a future desert world. Atmospheric pressure crashed from comfortable Earth-like levels down to just 0.1 atmospheres, a 90% reduction that fundamentally altered the physics of water stability on the planetary surface. This Stage 2 collapse marked the beginning of the end for Mars's magnificent ocean systems. liquid water began its irreversible migration from Martian seas into the vacuum of space. The 0.1 atmosphere pressure level represents a cosmic point of no return for planetary water systems. At this reduced pressure, the temperature range for stable liquid water shrinks dramatically, from Earth's comfortable 100-degree span down to just a few degrees around the water triple point. Mars essentially entered a narrow environmental zone where liquid water could exist only under perfect temperature conditions, conditions that became increasingly rare as climate continued deteriorating. This pressure collapse triggered massive changes in Mars's water cycle that began the planet's transformation from ocean world to desert monument. Surface water that had remained stable for hundreds of millions of years suddenly became vulnerable to rapid phase changes. During warm periods, liquid water would boil violently as reduced atmospheric pressure lowered the boiling point. During cold snaps, the same water would freeze instantly as the narrow liquid stability zone disappeared entirely. The atmospheric pressure crash accelerated water loss through multiple devastating mechanisms working in cruel combination. Direct evaporation increased as boiling points dropped below surface temperatures in many regions. Water vapor in the atmosphere became more vulnerable to escape processes as the thinning atmosphere provided less protection against solar radiation bombardment. The reduced atmospheric mass meant that water molecules needed less additional energy to achieve escape velocity. Mars's northern ocean began experiencing the first signs of systematic retreat during this Stage 2 collapse. Coastal regions that had maintained stable shorelines for millions of years started showing seasonal variations. Water levels fluctuated with temperature changes. Some shallow ocean areas began experiencing periodic dry spells as atmospheric pressure variations temporarily pushed water past stability thresholds. The feedback loops that had operated slowly during Stage 1 atmospheric loss now accelerated with frightening efficiency. Reduced atmospheric pressure made water vapor escape more likely. This decreased atmospheric humidity, which reduced greenhouse heating, which cooled surface temperatures. Cooler temperatures made liquid water less stable, which accelerated water loss to space. Mars entered a death spiral of environmental collapse that fed upon itself. Volcanic outgassing, which had previously helped maintain atmospheric stability by replenishing lost gases, could no longer keep pace with accelerating atmospheric escape. The planet's volcanic systems were already beginning to slow down as internal cooling progressed. Just when Mars needed maximum atmospheric replenishment to counteract mounting losses. The timing could not have been worse for the red planet's environmental survival prospects. Stage 2 water migration represented the beginning of the most massive environmental tragedy in solar system history. Over the following hundreds of millions of years, Mars would lose an Atlantic Ocean's worth of liquid water to space, through mechanisms that became unstoppable once atmospheric pressure dropped below critical thresholds. The red planet had entered the terminal phase of its transformation from water world to cosmic wasteland. 3.5 billion years ago, Mars experienced the final devastating blow in its long environmental death process. Average global temperatures plummeted through the -20 degrees Celsius threshold, crossing into permanently frozen territory that would doom the planet's remaining ocean systems to become vast ice sheets. This Stage 3 collapse represented the final farewell between Mars and its liquid water heritage. a cosmic funeral for planetary habitability that has lasted billions of years. The temperature plunge to -20 degrees created surface conditions where liquid water could no longer exist under any natural circumstances. Even Mars's remaining equatorial regions, which had maintained slightly warmer temperatures during earlier stages of climate collapse, finally succumbed to planetary-wide freezing. The red planet essentially transformed into a cosmic freezer operating at temperatures that would instantly kill most Earth life forms. This final freeze didn't happen gradually over millions of years. It occurred with geological suddenness as multiple environmental failures reached critical points simultaneously. Atmospheric pressure had dropped so low that greenhouse heating became virtually non-existent. Volcanic activity had slowed to minimal levels. This eliminated atmospheric replenishment that might have maintained warmer conditions. The magnetic field remained permanently offline, ensuring continued atmospheric loss that prevented any possibility of climate recovery. Mars's magnificent northern ocean, which had dominated 40% of the planet's surface for hundreds of millions of years, began its transformation into the largest ice sheet in solar system history. The ocean didn't freeze uniformly. It created a complex system of ice layers, frozen brine pockets, and subsurface liquid zones. These would persist for millions of additional years before complete solidification occurred. The freezing process created massive geological upheaval as expanding ice generated pressures that cracked bedrock, creating the chaotic terrain features visible in Mars's northern regions today. Freeze-thaw cycles in remaining liquid pockets carved additional channels and valleys, adding final chapters to the geological record of Mars's water activity. The planet's surface became a fossil museum preserving evidence of its former aquatic glory. Stage 3 environmental collapse also eliminated Mars's remaining weather systems that had continued operating despite reduced atmospheric pressure. With surface temperatures locked below freezing everywhere on the planet, water vapor essentially disappeared from the atmosphere, except for trace amounts sublimating directly from ice deposits. Mars lost its last connection to the water cycle that had operated for nearly 1 billion years. The biological implications of this final freeze would have been catastrophic for any life forms that might have evolved in Mars's earlier aquatic environments. Temperatures of -20 degrees represent conditions that challenge even the most extreme Earth organisms adapted for cold environments. Any complex chemistry that might have developed in Mars's ancient oceans faced sudden termination as biological systems became literally frozen solid. Yet Mars didn't surrender every molecule of its water heritage during this final freeze. Massive quantities of H2O became permanently locked in polar ice caps, subsurface permafrost layers, and underground ice deposits that persist today. The planet essentially created a water archive preserving billions of tons of frozen ocean remnants, waiting beneath the surface like a planetary time capsule. This Stage 3 freeze marked the end of Mars's 1 billion-year journey from Earth-like paradise to cosmic wasteland. The planet that had once maintained comfortable temperatures, thick atmospheres, and vast ocean systems had completed its transformation into the frozen monument to environmental collapse that greets spacecraft arrivals today. Mars's water farewell process had finally reached its tragic conclusion after 3.5 billion years of slow-motion planetary death. While Mars struggles with cosmic inadequacy issues, Earth operates like a gravitational heavyweight champion that refuses to let anything escape its powerful embrace. Our planet tips the cosmic scales at a massive 5.97 times 10 to the 24 kilograms, roughly 9 times heavier than Mars's lightweight 6.39 times 10 to the 23 kilogram mass. This isn't just a numbers game for planetary ego contests. Earth's superior mass creates gravitational muscle that has been protecting our atmosphere and water for billions of years, while Mars's weak gravity allows many potentially valuable atmospheric additions to drift away into space. Earth's powerful gravitational grip holds onto essential molecules like oxygen, nitrogen, and water vapor with determined strength. The gravitational difference translates into surface gravity measuring 9.8 meters per second squared, compared to Mars's pathetic 3.7 meters per second squared. That means Earth's pull is almost 3 times stronger at keeping everything, including water, firmly anchored to the surface. This stronger gravity creates a much higher escape velocity for Earth. Atmospheric molecules need to achieve speeds of 11.2 kilometers per second, more than twice Mars's 5 kilometer per second requirement. Earth essentially operates maximum security atmospheric detention. Every gas molecule that ventures within its sphere of influence faces a much harder time escaping than from Mars's loose planetary custody. The energy difference becomes enormous when calculated across geological time periods. Mars's atmosphere has been slowly bleeding away into space for billions of years. Earth keeps most of its atmospheric molecules trapped, leading to stable pressure levels that support liquid water through multiple protective mechanisms that work in Earth's favor. Our planet's stronger gravitational field extends much farther into space, creating a larger gravitational sphere of influence that helps maintain atmospheric stability even when solar wind and cosmic radiation attempt to strip away molecules. This gravitational reach provides a protective buffer zone, preventing atmospheric particles from gaining enough energy to escape. Earth's gravitational muscle also affects the planet's ability to retain lighter gases like hydrogen and helium. While these gases can still escape through thermal processes, Earth's gravity slows the loss dramatically, allowing Earth to maintain a complex atmosphere with multiple layers in composition, rather than losing everything to space like Mars's thin, wimpy atmospheric remnant. The atmospheric retention advantages extend to protecting against water loss specifically. Water molecules in the upper atmosphere can be broken apart by ultraviolet radiation, creating hydrogen that wants to escape. Earth's gravity makes it harder for that hydrogen to reach escape velocity, helping maintain the planet's water inventory over geological timescales. Protection that Mars's thin atmospheric envelope cannot match. But Earth's mass advantage created additional protective benefits beyond just atmospheric retention. The stronger gravity helps maintain internal heat longer, supporting geological activity and magnetic field generation, both of which create additional layers of water protection. Earth's gravitational dominance also affects the stability of our planet's orbit and rotation. The massive Earth provides inertial stability that helps maintain consistent seasonal patterns, preventing the dramatic climate swings that could destabilize water systems. Mars's smaller mass makes it more vulnerable to orbital perturbations and rotational changes that can create environmental chaos. This 9 times greater mass advantage represents one of the most fundamental differences between Earth and Mars. It created the gravitational foundation for billions of years of environmental stability and water protection. While Mars remained a lightweight planetary system, unable to hold onto the atmosphere and water it needed for long-term habitability. Earth's magnetic field represents one of the most reliable planetary protection systems ever created. While Mars's magnetic field died billions of years ago, leaving the planet naked against solar wind assault, Earth's magnetic shield has been operating continuously for 4.6 billion years without a single service interruption. This electromagnetic protection system generates a field strength ranging from 25 to 65 microteslas, creating a protective bubble extending over 60,000 kilometers into space. This massive magnetic cocoon deflects charged particles from the solar wind, preventing them from directly stripping away Earth's atmosphere and water molecules. Mars once had a magnetic field too, but its smaller size and faster cooling caused its internal dynamo to shut down early in its history. The planet's core solidified, the magnetic field collapsed, and Mars lost its primary defense against solar radiation. Earth maintained its internal heat, keeping its liquid iron core churning and generating magnetic protection for billions of additional years. The magnetic field works like an invisible force field. It guides charged particles around Earth rather than letting them slam directly into the atmosphere. Solar wind particles that would otherwise blast atmospheric molecules into space get diverted toward the polar regions, creating aurora displays instead of atmospheric destruction. When charged particles do penetrate the magnetosphere, they get funneled into specific regions rather than hitting everywhere. This concentration effect means most of Earth's atmosphere remains protected from direct particle bombardment. Mars had to endure solar wind attacks across its entire surface, leading to gradual atmospheric erosion over geological time. The magnetic field also prevents water molecules from being broken apart and lost. Solar radiation can split water vapor in the upper atmosphere into hydrogen and oxygen. The hydrogen tends to escape to space. Earth's magnetic field reduces the amount of radiation reaching the upper atmosphere, slowing this water loss process significantly. Mars experiences much higher rates of atmospheric ionization. Its upper atmosphere gets bombarded by solar particles that strip electrons from molecules, creating ions that can be swept away by the solar wind like cosmic dust. Earth keeps most of its atmosphere neutral and stable, because the magnetic field prevents this ionization from occurring at destructive levels. The magnetic field extends protection far beyond the atmosphere itself. It creates a magnetosphere that deflects cosmic rays and solar energetic particles. These high-energy particles can penetrate deep into the atmosphere, breaking apart molecules and creating chemical reactions that degrade atmospheric stability. Earth's magnetic shield reduces this particle flux, maintaining atmospheric chemistry that supports water retention. During periods of intense solar activity, like coronal mass ejections, the magnetic field becomes even more crucial. These solar storms can blast planets with massive particle clouds. Mars gets hit directly, potentially stripping significant amounts of atmosphere during each major storm event. Earth deflects most of these particles, preserving its atmospheric integrity through solar storm seasons that would devastate an unprotected planet. The 4.6 billion year endurance of Earth's magnetic field represents remarkable planetary engineering. It requires a stable internal heat source, a liquid metallic core, and sufficient rotation to drive the dynamo effect. Earth maintains all these conditions. Mars lost them, creating one of the most decisive differences in planetary habitability. Without this magnetic protection, Earth's atmosphere would have been gradually stripped away like Mars's. Water would have been lost to space, and the planet would have become a barren world. Instead, Earth's magnetic field has provided uninterrupted protection, allowing water to remain stable on the surface for billions of years, supporting the complex climate and water cycle systems that make Earth uniquely habitable. Earth won the ultimate cosmic real estate lottery by securing the premium 1.0 AU location in our solar system's habitable zone, while Mars got stuck in the cosmic suburbs at 1.5 AU, too far from the Sun to maintain stable liquid water without extreme atmospheric greenhouse effects. This prime solar real estate location has been delivering consistent energy input for billions of years, creating surface temperatures that remain in the sweet spot, neither too hot nor too cold, just right for liquid water stability over geological timescales. Earth receives about 2.3 times more solar energy than Mars. This energy advantage means Earth's surface can maintain temperatures above freezing more easily, supporting liquid water oceans and a dynamic water cycle. Mars struggles to maintain temperatures above water's freezing point, even with a thicker atmosphere. The energy advantage of Earth's location becomes starkly apparent when considering atmospheric greenhouse effects. Mars would need a much thicker atmosphere to trap enough heat to maintain liquid water. But Mars cannot retain such an atmosphere due to its weaker gravity, creating a planetary catch-22. Earth's optimal distance means it doesn't need extreme greenhouse warming. Our planet can maintain liquid water with a moderate atmosphere that Earth can actually hold on to. Mars needs more atmospheric warming, but cannot keep the atmosphere required, leading to a cold, dry world where water freezes or sublimits. The 1.0 AU position also provides more stable seasonal patterns. Earth receives relatively consistent solar energy throughout its orbit because of its low orbital eccentricity and stable axial tilt. Mars experiences more extreme variations due to its more eccentric orbit and unstable tilt cycles. Earth's orbit maintains an eccentricity of just 0.017, creating minimal seasonal variations in solar distance. Mars has a 0.093 eccentricity. That creates dramatic seasonal distance changes. These orbital differences mean Mars experiences larger temperature swings, more extreme seasonal conditions, and greater challenges maintaining stable liquid water environments. Earth enjoys orbital stability, providing consistent conditions for water cycles and climate regulation. Earth's position also allows for a stable atmospheric pressure regime. At 1.0 AU, water can exist as liquid across a wide range of pressures and temperatures. Mars's location means water-vapor pressure relationships become more challenging, making it harder for water to remain liquid even when temperatures rise above freezing. The Goldilocks zone represents a relatively narrow band of distances, where liquid water can remain stable. Earth sits comfortably within this zone. Mars sits near the outer edge, where small changes in atmospheric pressure or solar output can push conditions away from habitability. This distance difference affects everything about planetary climate. Earth receives enough energy to drive weather systems, ocean currents, and a robust water cycle. Mars receives less energy, leading to weaker atmospheric circulation, less weather, and limited water cycling. The 1.5 AU distance also means Mars experiences lower atmospheric temperatures. That reduce the atmosphere's ability to hold water vapor, leading to water being trapped as ice rather than cycling through the atmosphere and surface. Earth's optimal solar distance has remained stable for billions of years. The Sun's output has increased slowly over time, but Earth's position allows for climate adaptation through atmospheric composition changes. Mars's marginal position makes it harder to adapt to changing solar conditions. This simple distance difference of 1.5 times farther from the Sun created cascading effects. Mars became too cold for stable surface water, too dry for active water cycles, and too energetically starved to maintain the environmental systems that support liquid water. Earth's 1.0 AU position provided the energy foundation for maintaining water stability and habitability for billions of years. Earth's orbital and rotational stability provides another crucial layer of water protection. While Mars experiences dramatic climate swings and orbital chaos, Earth maintains remarkably consistent conditions over geological time. Earth's stable axial tilt of about 23.5 degrees creates predictable seasons. Mars's tilt varies wildly between 0 and 60 degrees over long timescales. This tilt chaos creates extreme climate oscillations, making it nearly impossible for Mars to maintain stable water environments. When Mars's tilt becomes extreme, polar ice can sublimate rapidly, creating temporary atmospheric thickening, but when tilt decreases, the atmosphere collapses again, trapping water and carbon dioxide at the poles. This cycling prevents long-term atmospheric stability, constantly disrupting any potential water systems. Earth avoids this chaos thanks to our large moon. The moon stabilizes Earth's axial tilt, preventing the wild variations that plague Mars. This lunar stabilization keeps Earth's climate relatively consistent, allowing water to remain stable on the surface. Earth's orbit is also much less eccentric, creating minimal variations in solar distance throughout the year. Mars's more elliptical orbit creates significant changes in solar energy received, leading to stronger seasonal effects and more unstable climate patterns. These orbital and rotational stability factors create a climate system that can maintain liquid water consistently. Mars gets periodic bursts of better conditions, followed by long periods of worse conditions, preventing the sustained stability that water-based life requires. Earth's stable seasons allow for predictable water cycling, rain patterns, river flows, ocean currents, and long-term climate regulation. Mars's chaotic variations would constantly disrupt these systems, making it difficult for water to remain in stable liquid reservoirs. The stability advantage becomes especially important over millions of years. Earth's predictable conditions allow ecosystems to develop and adapt. Mars's unpredictable swings would repeatedly wipe out any developing water-based systems, resetting environmental conditions before complexity could emerge. This orbital and rotational stability represents another crucial factor. It helps explain why Earth maintained water, while Mars lost its water to freezing, sublimation, and atmospheric collapse cycles driven by orbital chaos. Earth's atmosphere represents a perfectly balanced chemical recipe. It provides thermal protection and water stability. Mars never achieved anything close to this atmospheric engineering success. Earth's atmospheric pressure of 1 atmosphere creates conditions where liquid water can exist across a wide temperature range. Mars's 0.6% atmospheric pressure provides virtually no pressure protection, Water on Mars either freezes or boils away rapidly because the atmospheric pressure is too low to support stable liquid phases. Earth's atmospheric composition also provides thermal insulation. Nitrogen makes up 78% of our atmosphere, providing bulk pressure without excessive greenhouse heating. Oxygen provides 21%, supporting complex chemistry and life processes. This balance creates a thermal blanket effect, smoothing out temperature extremes. Mars's thin atmosphere provides almost no thermal buffering. Day-night temperature swings on Mars can exceed 100 degrees Celsius. Because there is not enough atmosphere to retain heat, Earth experiences much smaller temperature swings, thanks to atmospheric heat capacity and greenhouse regulation. The atmosphere also enables Earth's water cycle. It can hold water vapor, transport moisture around the planet, and create precipitation systems. Mars's atmosphere cannot hold much water vapor, limiting water transport and precipitation, preventing an active water cycle from maintaining surface water reservoirs. Earth's atmospheric pressure also prevents water from sublimating directly from ice to vapor. At Earth's pressure, ice melts to liquid first, creating stable liquid water reservoirs. Mars's low pressure allows ice to sublimate directly, making it harder to maintain liquid water even when temperatures rise. Earth's atmosphere also protects against radiation. It blocks harmful ultraviolet rays and provides shielding against cosmic rays. This radiation protection helps prevent water molecules from being broken apart. Mars's thin atmosphere provides minimal radiation shielding, allowing more water destruction through photochemical processes. The thermal blanket effect becomes crucial during cold periods. Earth's atmosphere retains enough heat to prevent global freezing, even during ice ages. Mars lacks this thermal buffering, making it prone to complete atmospheric collapse and extreme cold conditions. Earth's atmospheric stability also supports long-term climate regulation. The atmosphere interacts with oceans and geology, creating feedback systems that maintain temperature stability. Mars's thin atmosphere cannot support such complex regulation, leading to climate extremes that destabilize water systems. This atmospheric recipe represents the final layer of protection. Earth maintained the pressure, composition, and thermal properties needed for long-term liquid water stability. Mars never developed a comparable atmospheric system, making water retention nearly impossible over geological time. Earth's one-atmosphere thermal blanket creates surface conditions where liquid water can exist across enormous geographic ranges, supporting oceans, lakes, rivers, and groundwater systems. Mars could never achieve this atmospheric stability, leading to its transformation into a cold desert world where water exists mainly as ice and occasional vapor. This atmospheric protection system works together with Earth's gravity, magnetic field, and orbital stability, creating a comprehensive water protection package that has operated successfully for billions of years. While Mars lost each of these protective layers, one by one, the result is the dramatic difference we see today. Earth remains a blue planet covered in liquid water. Mars became a red planet with only traces of water locked away in ice caps and underground deposits. Earth's protective systems operated as a coordinated defense, keeping water stable, maintaining atmosphere, and preserving habitable conditions. Mars's systems failed sequentially, leading to water loss, atmospheric collapse, and environmental degradation that turned a potentially habitable world into an uninhabitable desert. These 5 decisive differences explain why Earth could protect its water, while Mars lost most of its water inventory to space, freezing, and geological sequestration. Earth had the right mass, the right magnetic field, the right solar distance, the right orbital stability, and the right atmosphere. Mars missed out on each of these advantages, creating a perfect storm of planetary failure that left it dry, cold, and hostile, while Earth remained a thriving water world capable of supporting complex life and diverse ecosystems. The story of Earth and Mars reveals how multiple factors must align perfectly for long-term water stability. It's not enough to have water initially. A planet must have the protective systems to keep water from escaping, freezing permanently, or being destroyed by radiation and solar wind. Earth's success represents an extraordinary combination of planetary properties, working together to maintain water and habitability for billions of years. Mars's failure shows how losing even one key protective system can trigger cascading losses, leading to planetary desiccation and the end of surface habitability. These protective differences continue operating today, keeping Earth's water stable and accessible, while Mars remains a cautionary tale of planetary vulnerability, showing what happens when a world cannot protect its most precious resource: liquid water. And these same principles help us understand what to look for in exoplanets. When searching for other worlds that might protect their water and maintain habitable conditions, like Earth has done so successfully. Earth's water protection story is ultimately a story of planetary defense systems. Multiple layers of protection working in harmony, creating a stable environment where water can persist and where life can thrive for billions of years. Mars had water once, but it lacked the complete protection package, and over time it paid the price, losing the water that could have made it a second blue world in our solar system. Earth remains unique in our solar system, not just because it has water, but because it has the protective systems needed to keep that water stable, accessible, and cycling through complex environmental processes that support life. These 5 decisive differences created the foundation for Earth's diverse ecosystems and complex water cycling systems that Mars lost when its atmospheric pressure collapsed below critical thresholds billions of years ago. Despite losing its magnificent oceans billions of years ago, Mars has been quietly hoarding water like a cosmic survivalist. It is preparing for the ultimate planetary emergency. Hidden beneath the red planet's dusty surface and locked away in gleaming polar ice caps lies the largest water stockpile in the inner solar system outside of Earth. Roughly 1,001 trillion tons of frozen H2O waits for someone clever enough to unlock this planetary treasure chest. The polar ice caps alone contain approximately 1 trillion tons of water ice mixed with frozen carbon dioxide. They create massive reservoirs that dwarf many of Earth's freshwater supplies. These gleaming white caps visible from Earth represent just the visible portion of Mars's water savings account. It is the equivalent of finding a planetary-scale iceberg, with most of the wealth hidden below. But the real jackpot lies underground. Mars has been secretly banking water for millions of years as subsurface permafrost. It extends across vast regions of the planet. Recent radar surveys have revealed underground ice deposits containing roughly 1,000 trillion tons of frozen water. That is enough to cover the entire planet in an ocean 6.8 meters deep. That would require melting it and distributing it evenly across the Martian surface. These underground ice vaults are not scattered randomly across the planet like loose change under cosmic couch cushions. The permafrost concentrates in specific geographic zones. Ancient climate conditions created optimal freezing environments there. Some deposits reach thicknesses exceeding 100 meters. They are essentially underground glaciers kept in cold storage for millions of years. The purity of these ice reserves would make any water treatment engineer jealous. Earth's groundwater often requires extensive purification. Mars's subsurface ice formed from ancient precipitation and atmospheric moisture. That moisture froze before contamination could occur. These deposits represent fossilized weather from Mars's former water world era. Prehistoric ice cream that never melted and never spoiled. Accessing this frozen fortune would not require sending mining expeditions to Mars's distant polar regions. Much of the subsurface ice sits just 1 to 2 meters below the surface across mid-latitude zones. These are zones where human settlements would most likely establish operations. Future Mars colonists could literally dig for water in their backyards, rather than hauling it across continents from polar ice caps. The combined water reserves locked in Mars's polar caps and underground ice deposits contain roughly 100 times more water than all the rivers on Earth combined. That represents enough raw material to potentially recreate substantial water systems across Mars's surface. This would require technology and energy sources to excavate, melt, and redistribute this planetary water inheritance. Yet these trillion-ton water stockpiles remain tantalizingly out of reach using current technology. Melting and mobilizing even a small fraction of Mars's ice reserves would require energy inputs equivalent to the total power consumption of human civilization for decades. Mars essentially operates a cosmic bank account with enormous frozen assets. But there is no practical way to make withdrawals using existing technology. Scientists have proposed what might be the most audacious engineering project in human history. It would construct an artificial magnetic field generator powerful enough to shield the entire planet Mars from solar wind bombardment. This cosmic umbrella would require building magnetic field generators comparable in size to the International Space Station. They would be positioned at Mars's L1 Lagrange point. They would create a protective electromagnetic barrier spanning millions of cubic kilometers of space. The engineering specifications for this planetary protection system read like science fiction becoming reality. The artificial magnetosphere would need to generate magnetic field strengths thousands of times stronger than typical spacecraft magnetic systems. It would create an electromagnetic barrier powerful enough to deflect solar wind particles traveling at over 400 kilometers per second. Think of it as a cosmic force field that operates on planetary scales. It would protect a planet rather than a spacecraft. The magnetic shield would operate by positioning massive electromagnetic generators roughly 320,000 kilometers upstream from Mars. This would be at the L1 Lagrange point. The artificial magnetosphere could remain stationary relative to Mars there. It would intercept incoming solar wind. The magnetic field generators would create a protective shadow zone downstream. Mars could shelter from cosmic bombardment there, like a planet hiding behind an electromagnetic umbrella. Recent computer simulations suggest this artificial magnetic field approach could actually work. It would require technology that is theoretically achievable using advanced versions of current electromagnetic systems. The key breakthrough involves superconducting magnetic coils. They would generate field strength several thousand times more powerful than Earth's natural magnetic field. They would be powered by nuclear reactors or advanced solar energy collection systems. The protective effects of an artificial magnetosphere could begin restoring Mars's atmospheric stability within decades. That is far faster than geological timescales. By stopping ongoing atmospheric loss to solar wind bombardment, the magnetic shield would allow Mars's remaining atmosphere to begin thickening. This would happen through natural volcanic outgassing and sublimation from subsurface ice deposits. The planet could begin atmospheric recovery for the first time in 4 billion years. But the construction challenges for this cosmic protection project would dwarf any engineering achievement in human history. The magnetic field generators would require launching thousands of tons of superconducting materials, nuclear reactors, and electromagnetic equipment to Mars's L1 point. This logistics effort would make the International Space Station look like a backyard shed construction project. The energy requirements alone would challenge human technological capabilities for decades to come. Maintaining magnetic field generation powerful enough to protect an entire planet would consume energy equivalent to major Earth cities operating continuously. The artificial magnetosphere would require a planetary-scale utility company operating in deep space. It would need perfect reliability for centuries. Yet the artificial magnetic field approach represents one of the most promising terraforming technologies. It addresses Mars's fundamental atmospheric loss problem directly. Unlike schemes that thicken Mars's atmosphere while ignoring ongoing atmospheric escape, the magnetic shield would stop the bleeding first. Then it would attempt atmospheric rehabilitation. It is cosmic emergency medicine applied to planetary environmental collapse. The timeline for deploying artificial magnetic field protection could theoretically begin within this century. That depends on humanity committing the resources for such an ambitious project. Unlike schemes that require centuries of atmospheric modification, the magnetic shield could start protecting Mars within decades of construction completion. That assumes political will and economic resources for the largest engineering project ever attempted. Imagine turning Mars into a planetary greenhouse. You would pump its atmosphere full of heat-trapping gases. The red planet would warm enough to prevent water from instantly freezing on the surface. Scientists have calculated that increasing Mars's atmospheric carbon dioxide concentration by roughly 100 times current levels could raise global temperatures by approximately 5 degrees Celsius. That could transform Mars from a cosmic freezer into a merely uncomfortably cold planet. Liquid water might occasionally survive. The greenhouse effect multiplication strategy would exploit atmospheric physics. It helped maintain Mars's ancient warm climate billions of years ago. Carbon dioxide molecules absorb infrared radiation and trap heat in planetary atmospheres through well-understood greenhouse mechanisms. By dramatically increasing CO2 concentrations, Mars could theoretically recreate the atmospheric greenhouse heating that once supported its ocean systems. But achieving 100 times current CO2 levels would require adding roughly 2,000 trillion tons of carbon dioxide to Mars's existing atmospheric inventory. That represents more gas than exists in all of Earth's fossil fuel deposits, coal reserves, and carbonate rock formations combined. Mars would need to import carbon dioxide equivalent to Earth's entire carbon cycle. that would be required to achieve sufficient greenhouse gas concentrations. Several potential sources could theoretically supply this massive CO2 requirement, though none approach practicality using current technology. Mars's polar ice caps contain substantial frozen carbon dioxide. It could be sublimated into the atmosphere through targeted heating. Subsurface carbonate minerals might release CO2 through chemical processing or thermal treatment. Even importing carbon from asteroids or comets represents a theoretical possibility for sufficiently advanced civilizations. The engineering challenges for atmospheric CO2 enhancement would require industrial operations on scales never before attempted. Sublimating Mars's polar dry ice deposits would demand heating systems that process millions of tons annually for decades. Chemical processing of carbonate rocks would require mining and refining operations spanning entire continents. It would consume energy exceeding Earth's total industrial capacity. The greenhouse warming approach also faces fundamental atmospheric physics limitations. These could prevent success regardless of technological capabilities. Mars's thin atmosphere allows significant heat loss through radiation to space. This might counteract greenhouse heating effects. The planet's distance from the Sun means that even enhanced greenhouse effects might prove insufficient. They might not maintain stable liquid water conditions. Atmospheric modeling suggests that even successful CO2 multiplication might create only temporary warming. It could reverse if atmospheric loss mechanisms continue operating. Without addressing Mars's fundamental atmospheric escape problems through magnetic field restoration or other protection systems, enhanced greenhouse gases might simply escape to space faster than they could be replenished. That would happen through industrial processes. The 5-degree temperature increase projected from CO2 multiplication would represent significant progress toward making Mars more hospitable, but it would not solve the planet's fundamental water stability problems. Surface temperatures would rise from -60 degrees Celsius to -55 degrees. That is still well below freezing for most locations and seasons. Mars would become slightly less deadly rather than actually habitable. Yet the greenhouse enhancement approach represents one of the more technically achievable terraforming strategies. It works with atmospheric physics rather than against fundamental planetary limitations, unlike schemes that require altering Mars's gravity, orbital distance, or planetary mass. Atmospheric modification exploits well-understood greenhouse mechanisms. These mechanisms definitely work under the right conditions. The question remains whether humanity could ever marshal the industrial capacity necessary to implement atmospheric CO2 multiplication on planetary scales. Even the most optimistic terraforming enthusiasts acknowledge that transforming Mars into a genuinely habitable world would require a minimum of 500 years, using technology that doesn't exist yet and might never become practical. This isn't pessimistic speculation. It's mathematical reality based on the enormous scales involved in planetary environmental engineering and the fundamental physics limitations that govern atmospheric and climate modification processes. The 500-year timeline assumes that humanity develops magical levels of technological capability, including fusion-powered industrial systems, self-replicating robotic manufacturing, and energy production exceeding current global capacity by factors of thousands. Even with these optimistic assumptions, the sheer volume of required materials and energy is enormous. Atmospheric modification, magnetic field restoration, and water redistribution would consume centuries of continuous industrial effort. Consider just the timeline for atmospheric pressure restoration. Mars currently maintains 0.6% of Earth's atmospheric pressure, meaning the planet needs roughly 167 times more atmospheric mass to achieve Earth-like conditions. Adding this much atmospheric material through any known process would require processing billions of tons of source materials annually for centuries. No conceivable industrial system could operate at the scales necessary for faster atmospheric rehabilitation. The energy requirements alone would challenge any civilization's technological capabilities across multiple centuries. Melting Mars's subsurface ice deposits and sublimating polar CO2 reserves would require immense energy. Constructing artificial magnetic field generators and maintaining planetary-scale industrial operations would consume energy equivalent to thousands of times humanity's current global power production. Mars terraforming would essentially require building a solar system-scale industrial economy focused entirely on planetary modification. The technical challenges multiply when terraforming projects must operate simultaneously rather than sequentially. Magnetic field restoration, atmospheric thickening, greenhouse gas enhancement, and water redistribution all need to proceed together. This prevents environmental modifications from canceling each other out. Coordinating multiple planetary-scale engineering projects across centuries would require organizational capabilities that exceed anything humans have ever achieved. Even optimistic terraforming timelines assume that fundamental technical breakthroughs occur on schedule without major setbacks, cost overruns, or technological dead ends. Real engineering projects routinely exceed initial cost and schedule estimates by factors of 2 to 10 times original projections. Applied to terraforming scales, normal engineering uncertainties could easily extend project timelines from 500 years to multiple millennia. The 500-year minimum timeline also assumes that Mars's environmental systems would respond predictably to human modifications. It assumes no unexpected feedback effects or system failures. Planetary climate systems involve complex interactions that could produce unintended consequences from terraforming efforts. Mars might resist environmental modification in ways that current atmospheric models cannot predict. Economic sustainability represents another challenge that could extend terraforming timelines indefinitely. Maintaining planetary-scale industrial operations for centuries would require economic productivity and resource allocation that exceeds any historical precedent. The civilizations sponsoring Mars terraforming would need to maintain focus and funding across time periods longer than most human institutions have ever existed. Political continuity across timescales over 500 years poses equally daunting challenges for terraforming project management. Human political systems rarely maintain consistent policies across decades, let alone centuries. Mars terraforming would require unprecedented international cooperation and political stability. It would extend across multiple centuries without major conflicts, economic collapses, or changes in civilizational priorities. The harsh mathematical reality suggests that Mars terraforming represents an engineering challenge so enormous that success remains questionable regardless of technological advancement. The physics and scale requirements may simply exceed what any planetary civilization could realistically accomplish. It would make Mars terraforming more fantasy than an achievable engineering goal. Despite overwhelming technical challenges and centuries-long timelines, The vision of transforming Mars into a blue water world continues, inspiring human imagination and driving our species' expansion into the cosmos. This dream of planetary resurrection brings liquid oceans back to a world that lost them billions of years ago. It represents perhaps the most ambitious expression of human technological optimism and our species' refusal to accept environmental limitations as permanent constraints. The Blue Mars vision captures something fundamental about human nature that transcends practical engineering considerations. We're the species that drained swamps, built cities in deserts, and constructed artificial islands where none existed before. Terraforming Mars represents the ultimate expression of humanity's conviction that environmental problems have engineering solutions. If we're willing to invest sufficient creativity, resources, and determination across whatever timescales prove necessary. Modern Mars colonization scenarios increasingly embrace partial terraforming approaches that could create localized habitable zones rather than transforming the entire planet. These paraterraforming concepts envision enclosed habitable areas protected by artificial barriers and atmospheric systems. They create Earth-like environmental conditions across limited geographic regions. Think of them as massive greenhouse complexes that could eventually expand into continent-sized habitable zones. The psychological appeal of Blue Mars extends beyond mere human expansion into space. It represents hope for environmental redemption and proof that even planetary-scale environmental collapse doesn't constitute permanent defeat. If humanity could restore water to Mars, it would demonstrate our species' capacity to repair environmental damage regardless of scale or complexity. Mars terraforming represents environmental optimism applied to cosmic scales. Advanced civilization scenarios suggest that Mars terraforming might become achievable once humanity develops sustainable fusion energy, robotic manufacturing systems, and space-based industrial capacity that operates independently of Earth's resource limitations. These technological capabilities would represent a transition from planetary civilization to truly spacefaring civilization, with access to solar system-scale resources and energy. The terraforming vision also drives technological development that benefits humanity regardless of whether Mars modification proves practical. Research into atmospheric engineering, climate modification, and planetary protection systems advances human understanding of environmental management techniques that could prove crucial for maintaining Earth's habitability during future environmental challenges. Mars serves as a natural laboratory for testing planetary engineering concepts that might eventually become necessary for protecting Earth. This could help protect Earth from climate instability, asteroid impacts, or other environmental threats. Learning to restore atmospheres, modify planetary climates, and manage water systems could provide insurance against environmental catastrophes. These catastrophes might threaten human civilization on our home planet. The Blue Mars dream represents humanity's longest-term thinking about our species' future in the universe. Most human planning operates across decades or at most centuries, but terraforming requires civilizational thinking across millennia. The vision forces us to consider what kind of species we want to become and what legacy we want to leave across cosmic timescales. Even if Mars terraforming never becomes practical, the attempt would likely produce technological and organizational capabilities that transform human civilization. This could justify the effort regardless of planetary engineering outcomes. the journey toward Blue Mars might prove more valuable than the destination. It would advance human capabilities in space technology, environmental management, and international cooperation. This cooperation enhances our species' long-term survival prospects. The dream of restoring water to Mars connects our species to something larger than individual human lifespans or even civilizational timescales. It represents humanity's participation in cosmic evolution and our potential role in spreading life and consciousness throughout the universe. Blue Mars embodies our species' cosmic ambition and our refusal to accept that dead worlds must remain dead forever.